What about the audio? Does the audio go through your GoToMeeting?
I can share the audio on my side and pick up the mic, so I can share that.
Oh, good. If you can share that while I share the video? Good. That would be the way to do it. Let's try it. Be less clunky transitions that way. Good.
Test, 1, 2, 3, test, test, test. All right, I got to turn this one off. Over here. All right. Good morning, everyone. Welcome back. For those of you that took the effort to come back, appreciate it. I'll just do a couple quick reminders about the format again. Number one, the restrooms are out and around the corner. Hopefully folks online can hear all right, although I'm not moderating to check right now, so I would have no idea if you could or couldn't. Hopefully that's a fingers crossed. And then in addition, for those of you that are speaking and presenting today, since I think there may be some new folks in the room, have an X up here. This is mainly for the video camera so that we capture you in frame for the recordings that are going on. So if you can make sure that you stay relatively close to this, if you're going to move around a lot, if you can let us know so that we can at least pan and move the video camera to account for your wild body movements, then we will do our best to try and do that. Outside of that, I hope everyone had a good time yesterday. I'm going to start off really quickly with some stuff about the California V6 Task Force, sort of what we're up to, what's going on. I think I claimed to a few folks yesterday that I wasn't going to have any slides, but then I sort of felt like it was going to be awkward to have nothing up here. Sort of wanted to point out that there's actually other task force. Most of you know the Rocky Mountain V6 Task Force because they run one of the largest events that happens in North America. They have a very strong organization. The Texas event is actually really good. I know for Mexico and there are a few events that are going down in that neck of the woods. They're covered in the North American side, so believe it or not, we have stuff that happens down there. Canada, I haven't seen anything happen in years. I'll have to give Bruce a hard time because I don't think I've seen anything there. Yeah, Mid-Atlantic hasn't had anything in a long time either. And Hawaii, I know Hawaii has a few things that go on, but they really don't let the rest of us know much about what's going on there. It's mainly on the academic side. They don't want us to visit. University of Ottawa, they had an event? Okay, cool, good to know. So this is my contact information if anyone wants to reach out to me in regards to the California Task Force. So feel free to bug me on that. I just wanted to go over quickly what our purpose was. So advocacy being the principal one, right? So helping Bruce to host this sort of event to help get the word out about V6. Education, so events and local meetings. We do have a meetup group. So if you're on Meetup and you just search for the California V6 Task Force, we're going to be starting to generate out some regular meetings at some of the companies around the Bay Area. And then George will probably be doing some stuff up in Sacramento and Tom down in the Los Angeles region. So we're going to be trying to utilize those to do that. Hopefully we might be able to get a few white papers and content. Content generation is one of the things. That's why we support and do this event in conjunction with gogoNET. Also the workshops, so the sort of the labs, the hands-on workshops, that's part of the goal for what we're up to. And that's one of the reasons that we, the task force actually helps to coordinate the workshops that happen in the beginning. And then evangelism, so you guys sort of got to believe in all this, otherwise why the heck are you here? And so this is one of the principal reasons of doing what we're doing. On that, wanted to thank Bruce, although I think he's run around the corner to go work on something in the interview room, but thanks to Bruce for helping to put all this on. It takes a lot of effort. A lot of people don't realize how much running around and planning and everything else that goes on for doing this, so I really appreciate his time and effort to do that. Shout out to George. Unfortunately, he couldn't make it for the event, but he's been doing a lot of work on the backside to make sure that things are happening. Salman, who was here yesterday, is also really critical in making sure that we get workshop resources, everything else, and things of that nature. So with that, that's actually it for me. Next up, we're actually going to have, and I'll bring his deck up here in a second, is going to be Dave Thaler. Dave's going to be talking about Xbox, right? It doesn't get any better than talking about Xbox and gaming. So with that, I think we have, do we have the lav still? Do we have the lav mic as an option? Yeah, get that over to Dave. Give me half a sec, put this down.
All right. Let me make sure. Good. All right. Both mics working? So we can do Q&A with this one.
All right. All right, cool. So, Dave Taylor, how are you? Take the X.
Thanks, Ed. So, anybody here have an Xbox? Okay. Two? More than one Xbox? Okay. So I'm going to be talking about Xbox One, right? As I'm sure many of you know, Xbox One is due to be released with November 22nd. And yes, thank you. Anybody online or watching this remotely have an Xbox? Yeah, raise your hand. Okay, yeah, whatever. So I'm going to talk about Xbox One, but in order to do that, I'm also going to talk about IPv6, Teredo, and IPsec. And since we didn't do a deep dive into Teredo yesterday, to help you understand more about what the Xbox does, I'm going to be talking about Teredo for the first couple minutes here, and then I'll get into what Xbox One will do specifically. Now, when we talk about IPv6, right, one of the benefits of IPv6 we often talk about is this notion of I have end-to-end connectivity. Well, end-to-end connectivity is very important in peer-to-peer applications, right? And if you think about gaming, such as on the Xbox, peer-to-peer is a big part of that experience, right? And so that's one of the benefits that IPv6 brings to this peer-to-peer gaming notion. Same thing goes for IPsec, right? It's about end-to-end security, right? In your gaming experience, we want it to be secure as well. So one of the differences between what Xbox did and what Xbox One did is that Xbox One is all about IPv6. And so I'll talk about that. So Xbox One is an attempt to realize that promise, and one of their differences is that while Xbox used some proprietary custom things, Xbox One transitions to more of a standards-based mechanism. So the short version of all the rest of the presentation can be summarized into 3 bullet points, because what I want to help people understand is how do you get the best Xbox gaming experience, or how do you provide to others the best Xbox gaming experience, depending on what your role is. Okay? And so 3 bullet points I want you to remember. Number 1, provide IPv6 connectivity. Number 2, allow transition technologies such as Teredo to function, and we'll talk about that. And number 3, allow IPsec transport mode to function, and we'll talk about that. So with that, I'm going to jump into some of the protocol details and the history and future of Teredo, and then I'll come back to the relationship to Xbox after about 10 minutes probably. So when we talk about peer-to-peer, okay, we talked about this is one of the most common parts of gaming experiences, right? You're not just playing against the server, you're playing against your friends, your enemies, and so forth. Okay. Also, you often have sort of LAN play experiences where you have multiple Xboxes in the same location, but they may not be. They may be across the internet. Xbox 360 used a custom stun and security implementation. Okay. Now, stun is actually a standard. It was done by the same Behave working group that I was a co-chair of. For those of you not familiar with stun, it's a technology that's IPv4 based. Right? It's not just IPv4, but it's as widely used. It's meant for IPv4 to do rendezvous through a NAT, to say, oh, what's the address on the outside of your NAT so that I can talk to that and we can exchange IP addresses, and it's this fairly complicated mechanism. But as used today, it requires application changes to use a stun library, and it ends up using a separate port on the outside of every NAT. Meaning every connection that goes through it uses a separate port, just like normal NATs do. Okay? And so we talked about yesterday how once you start having a CGN, then you start running into port exhaustion issues. Okay? So one of the disadvantages of stun is that if your application is using a large number of ports, say one for every peer or at least one for every type of media to the same peer, right? Then you're going to be consuming one port in the external side of the CGN for every one of those. Then finally, yes, we want to move towards standards. We want to move towards things that you don't have to worry about custom rules. You just use the standard rules in middle boxes and ACLs and port rules and so forth. Okay. So when we look at IPv6 adoption today, okay, we usually talk about native IPv6. And we're talking about native IPv6 all the way to the end user in their house, okay? Including, does the Internet Gateway device, so that CPE, customer premises equipment, does that support IPv6 all the way to the boxes that are sitting behind it? And what we find today is that we're now all the way up to about 2%, I think, is the latest numbers in that range. About 2%, it's all the way, right? Otherwise, there's still some box in the middle of there, which means 98% of the time, there's some other box still in there that's not yet IPv6 capable, okay? So that means, so 2% is much higher than it was, and that will continue to increase, okay? But we have to work in a world where 98% of the connectivity isn't yet IPv6, but we still want to transition people to IPv6, okay? And so what we find is about 5% of the time, things are actually IPv6 capable. Okay, but for some reason, IPv6 is worse than the IPv4 for whatever reason. Okay, we talked about yesterday how tunnels is one example where your latency is much longer in some cases when you're using tunneling. Okay, but when you're talking about a peer-to-peer gaming experience, latency is everything, right? You get hit or something, you want that to be as fast and reliable as possible. So it's really the IPv6 preferred category, which is where IPv6 is at least as good as IPv4. It's either equivalent or it's better. Okay? So 5% of the time it's available, but only 2% of the time is it equivalent or better. And that's the 2% that would be using native IPv6. For all the rest of the cases, it means that IPv4 is either the only option or it's better than IPv6 significantly, either in terms of loss or in terms of latency. Okay? And that's where this technology called Trado comes in. So I'm now going to give you a short overview of Trado because, as we mentioned, this was what we expect to be used approximately 98% of the time. Okay. So Trado is an IPv6 transition technology that's a type of tunnel of IPv6 over IPv4, just to set some context. In fact, it's IPv6 over UDP over IPv4. And it uses a lot of the same techniques as the STUN protocol did. So when we talk about how STUN tries to figure out ports and stuff, Trado does all this too. But unlike STUN, which requires an application library, right? So I write my application, use this library, and then I figure out the ports, and I write my code to do that. Trado puts it all underneath IPv6, which means the application is written to just use IPv6. Okay? And then under the covers, the tunneling mechanism handles all that complexity, and it tunnels it over a single UDP port. Okay? Which means if I'm doing 4 types of media, right, I'm doing, an audio channel, and maybe I'm doing a webcam video channel, maybe I'm doing, some I hit you status reports and things. If all those are different TCP connections, they're still only using one port in that CGM, so it scales much better. Yeah, it's multiplexing, exactly. So in terms of Windows goes, Windows has already included this Trado functionality on by default ever since Windows Vista. Windows Vista, Windows 7, 8, 8.1 all include Trado on by default. And on by default doesn't mean it's used by default. It means it's this last resort that says if I don't have native and I don't have any other better type of tunnel, and I don't have any other type of IPv6, and I'm not in an enterprise that is that's firewalled or something where you actually don't want tunnels to be going in and out. If none of those are true, I'm just a consumer, I want IPv6 connectivity, then Trado can be used. But it does mean that we have many years of experience with Trado. Okay? And it's been improved and expanded for a number of years now. Now, as we've done that, we've gotten a bunch of feedback about what works and what doesn't work with Trado, what the problems are, what the benefits are, and I'll explain that in the next couple of slides. And so there's 2 things going on simultaneously which might at first glance sound opposite. Okay? And that's part of the point of this talk, is to explain, because you'll hear some things about Trado being bad and being sunsetting, and other things about things continuing to use Trado. And you're saying, and you might be thinking, well, how can those both be true? And that's what I want you to understand through this Trado part. Okay? So we're simultaneously sunsetting the Trado service for Windows hosts, and I'll talk about that, while simultaneously extending Trado support for Xbox One gaming scenarios. Okay? And I'm going to explain why the apparent contradiction actually makes sense. So when we talk about Trado, there's a couple different roles in the protocol. So in the top left, if you have an end-user device, such as a PC or a notebook or an Xbox, and in the bottom right, you have a Trado server. The role of the Trado server is to tell you your address. It's the thing that gives you your IPv6 address. It's the thing that facilitates packets sort of like ARP and neighbor discovery packets. It doesn't actually see any data traffic. It's basically the control traffic that says, by the way, think of it like, a DHCP server doesn't see any data packets, but it gives you configuration information, right? It helps you get bootstrapped. So the Trado servers help the clients configure their addresses, and they aid in figuring out what the external ports are that are available. Then across the top, you say, well, if I have a client that's using Trado, because he doesn't have native v6 connectivity, there's two types of entities he may be wanting to talk to. He may want to talk to entities on the IPv6 internet, right? Things in the top right have native v6 connectivity. Okay? We call that the IPv6 internet. And that communication goes through something that's called the Trado relay. Okay? It relays between native connectivity and a tunnel connectivity. Okay? So it's the thing that does the encapsulation and decapsulation in the middle of the path between two endpoints. You can also be talking to other devices that have Trado connectivity themselves, and so that's the bottom left, another end-user device, such as another Xbox or another Windows machine. And so Trado connectivity goes peer-to-peer, okay, directly being encapsulated in UDP directly between those two boxes without going through a relay. Okay? So again, the roles are the server, which doesn't see data, the relay, which is like a router in the middle of the path to the native v6 internet, and another client, which may talk directly peer-to-peer. Okay, so think of the red arrow at the top as the one that goes to the relay to the internet, and the blue arrow is the one that's going peer-to-peer, and this is where the distinction comes. This is in those two colors of arrows. So there's some good and there's some bad about Trado, meaning good experiences, bad experiences. All the bad experiences align with that red arrow on the previous slide. The ones that go through the relay is where the bad experiences go through. When trying to reach native IPv6 internet using Trado, there's a number of operational problems. This has been presented in much more detail in statistics and things by people like Jeff Houston. There's a link to it if you're interested in more information. But as we'll see, it's not directly relevant to Xbox, so I'm going to gloss over this, but to say this has approximately a 40% failure rate, trying to talk from a Trado client to a native v6 destination. Now, most of the time, that's compensated for by the address selection rules to say, well, I'm going to choose something like IPv4 rather than using Trado. So Trado is de-preferred, as I mentioned, it's a last resort. So even though it's bad, a lot of the times that it's bad, you wouldn't use it, you'd use something else, whether it's native v4, for example. And so the bottom line there is that Trado with relays is unreliable, and that's the part that we want to sunset. On the other hand, as a technology for doing peer-to-peer communication between two Trado-enabled clients, connectivity is actually really good. With basic matchmaking, that means you figure out which guy has Trado and you use Trado client to Trado client, right? As opposed to Trado client to somebody that has native v6. Then you get Trado connectivity at least 90% of the time. Okay? And 90% of the times as well, there's some things that are don't support UDP connectivity. You're behind some corporate firewall or whatever, so that's a couple percentage of that. Other percentage are NATs that are just plain broken, that just, stun wouldn't work either, right? So this percentage is about the same percentage that you'd get with stun. In some cases, it's slightly higher, as I mentioned, slightly better than the stun one because of the port sharing issues. And so this notion of peer-to-peer Trado has seen a lot of successful usage in more controlled environments. And by controlled environments, I mean things that don't need to get connectivity to the native v6 space, but are just Trado to Trado. An example of that is the direct access technology that I also mentioned in my talk yesterday, which is a remote access technology, such as getting into a corporate network. And so the blue line that we showed on the previous slide that goes between clients, usable, very usable. So remember the Trado servers. The Trado servers don't see data. They help get the addresses and the port information. I'm going to show you a couple stats here. Now, we don't keep specific telemetry about, specific individuals or things because, Microsoft is big on, privacy is important to us. But we know things about the aggregate Trado server load. And so that's what I'm going to talk about is how many packets, how many control packets go through the Trado servers and so on. So as somebody mentioned yesterday, I think it was Jeff, there's a popular BitTorrent client that actually uses Trado and IPv6 for similar reasons. Okay? And we saw a lot of the Trado usage spike when they started turning things on there. So this is the graph of control packets seen by the Trado server, which Microsoft operates. So the biggest Trado server is operated by Microsoft. The biggest Trado relay is operated by Hurricane Electric. Okay? And so this is from the server view. And so this is UDP datagrams per second, okay, at the Trado bank of servers. And so you see back in, December 2010 up to present, you have a steady increase. And somewhere in about a third of the way through, you see that big uptick there. That's about when the BitTorrent client got turned on and started using Teredo. Was it somewhere around August or October 11? Okay, so again, that's datagrams per second. And again, that's no data traffic whatsoever. That's just the control traffic. It's a very large number of clients using it. So Teredo's value is best realized when you put that together with something else that takes care of how do I know that the other guy is using a Teredo client? I'm using something else that's an invitation or matchmaking service, right? And so that's what Xbox One has. Right? The lobbying mechanism and stuff provides that matchmaking and rendezvous. Just having a tunnel IPv6 address and a tunnel Teredo address by itself, in particular, provides little value by itself and actually causes pain for developers. In other words, we ran an experiment, I think it's on the next slide we'll talk about, where we found that some apps have random behavior, right? Until the apps get fixed, then just putting on this extra Teredo address sometimes causes some apps to break and other ones to work. So what we've talked about is the proposed Teredo sunset plan, okay? This is relevant to IPv6 in general, is that we plan to deactivate those Teredo servers, ones we talked about, sometime in the first half of next year. Okay? Haven't announced an exact date yet. We're still trying to work out the operational plan there. But that's approximately when we expect to do that. We encourage the deactivation of the publicly operated Teredo relays. Again, that's the one that has at least a 40% failure rate, and so there's a lot of disincentive to use that. There's better mechanisms to access the native internet rather than using Teredo. Use other types of tunnels, tunnel brokers, and things. We will maintain separate Teredo servers, okay, for a separate class of things that are not trying to access the public internet, the public IPv6 internet, okay? Because even for the peer-to-peer connectivity, right, you still need Teredo servers to give out your Teredo addresses and find the ports, okay? So we're splitting that into two categories. The things that have been accessing the internet, which have been using the classic Teredo server bank, and a new server bank that's meant specifically for peer-to-peer connectivity, where if you use it, there's no expectation of access to the native v6 internet that way, okay? So by separating this bank, it makes it easier to manage and use tools to figure out what's going on between the two banks. Okay. So earlier this year, I think it was in June, we actually ran a test in cooperation with the v6 operations community. So we announced this like a month ahead of time, and we asked people to monitor stats and give us feedback on what they saw and so on. So we turned off the Teredo servers for a week just to see who would complain and what would break. But we told everybody ahead of time. And so then we presented this out at IETF 87, and what we got is lots of positive feedback. They said, you guys are going in the right direction. This is a great thing. Please continue on. And that's where we got to this plan sometime in the first half of 2014. Okay. There were some app compet issues. So we did find out some things that broke, and those are those apps that I talked about on the previous slide. Okay. And we know exactly which ones they are, the big ones anyway. And so we're working with them to make sure that they fix their bugs. So now with that as the background on Teredo, let's talk about Xbox One. Okay. Xbox One is all about the peer-to-peer part of Teredo. So Teredo by itself provides an IPv6 abstraction for peers. Okay? That means you don't write your application to use Teredo per se. You write your application to use IPv6. The platform itself takes care of making sure that IPv6 is done over Teredo. So combined with IPsec, okay, this provides straightforward application transparent, secure peer-to-peer connectivity. So what's important here is that, why do we use IPsec and not something like SSL? Okay. Well, two reasons. IPsec, number one, protects more than things like SSL because it operates at lower layers. You're protecting the IP addresses. You're protecting, the TCP headers and the sequence numbers and things, and they're all protected with IPsec. Number two, I mentioned with Stun, you have to use a separate application library and write your application to use Stun, where with Teredo you get that for free. Same thing goes with SSL. Usually if you're using SSL, you write your application to use an SSL library. If you're using IPsec, you don't do anything. It all happens at a lower layer. You get it for free. This is all about making the application developer's life easy by the platform doing as much as possible. This also allows them specifically to use UDP or TCP or whatever else. Okay? SSL by itself is usually TCP, but there is a DTLS form that works with UDP. Right? But here, IPsec means it's completely agnostic. You can use whatever protocol you want.
Which mode?
Which mode of IPsec? I mentioned that before. It's transport mode. It's always transport mode. Okay. So, stepping into some details of Xbox One. Number one is if you're using native IPv6, right, so that's that 2% case where an IPv6 is available and at least as good, if not better, than IPv4, okay, here's what happens. IPsec transport mode right here, okay, which means that it comes with an ESP option, and it uses IPv2 to negotiate sessions. Okay. Now, what guidance do we give for people doing administration of networks, for example? If you're administering a campus network or your own home network, or you have influence at an ISP, or you work at one, what do we tell people to do in, say, their consumer IGDs or the provider-managed cable boxes and so on? This is completely consistent with the RFC from the IETF on requirements for those boxes, the security requirements for those boxes. So there's basically two things, which is you'll get the best experience if you do the following two things. You'll get an experience if you don't, but you'll get the best connectivity. Okay. By best experience, that means that you will be able to serve as a host of sessions more, right? So when you go to a lobby, you get paired up with other people, and at least one of them has to be capable of being a host for a large number of people. Okay. And then other people can be clients of that, because most games are, one guy is acting as the host, and all the other ones are acting as clients of that host. Okay? And so by having the best experience, that means if you follow these, you can act as a host and be able to play games more with more people. Okay? Otherwise, you'll tend to be a client of people if you don't follow these. Does that make sense? Okay. So number one is to allow unsolicited inbound IPsec and IKE. Right? So you got a firewall that's there, but if that firewall allows IKE to go through to allow negotiation of stuff to go through that, once it's IPsec protected, then you'll get a better experience as if you don't allow that. Number two, that same RFC suggests that if you have one of those boxes that you're implementing or shipping or whatever, to have some mode where the users can disable the firewall capabilities. Maybe they put another box behind it or in front of it, okay, and they don't want the security boundary to be at that particular box. So making it important for an advanced user, a network administrator, to be able to configure which box it is that's a security boundary. Okay, so that was the case if you're just using native IPv6, which, as we mentioned, we expect to be about 2% of the cases based on the data right now. Okay, 2% and increasing, hopefully as fast as possible, as more people turn on IPv6 and native in their ISPs. Now, what we found that even today, sometimes Teredo is actually more reliable than native IPv6. Okay, why is that? Well, some IPv4 has been around for more than IPv6. Some people have boxes that still work better with IPv4 for one reason than another. Okay, or maybe routing is influencing a hiccup because some particular ISP interprets IPv6 as being in a faster supported mode than an IPv6 being in a trial mode or something. And since Teredo encapsulates everything over IPv4, okay, that means as the packet is traveling across the internet, it looks like IPv4 to most of those middle devices, and sometimes it'll get better behavior. Okay. And so many times today, Teredo is actually more reliable, meaning lower latency, less packet loss, than native IPv6 is. So what Xbox One actually does is it will be able to use three combinations of things. It can use Teredo client to Teredo client. So in that picture, that was the blue arrow. It can use native IPv6 to native IPv6. Okay, so if both sides have native IPv6, that's the 2%. Great. We hope it goes up from 2% as fast as possible. And then finally, it can use public IPv4 to public IPv4. Well, I should say IPv4 to IPv4. Okay, as long as there's no NAT in between. Okay, so the two cases are public IPv4 to public IPv4, which is going to be approximately 0% of the cases. Okay, or LAN play. You're both at home, and IPv4 is working great on your LAN, and for some reason, it's working better than IPv6 is. Okay? And so probably the biggest IPv4 cases will be LAN play. Okay? But notably, there is no case in which you have the Teredo client native. That was that red arrow that goes through a relay. Okay? That's part of what the matchmaking service does. It takes into account these three combinations and figures out what the best matches are. So, guidance for people who do IPv4 stuff in order to allow IPv6 to work great. Okay? So, support outbound UDP with a long port mapping. Okay? Again, most of these things just repeat what's in existing RFCs, but of course, not everybody reads RFCs, right? It's task forces and evangelism that we need, and that's why I'm presenting it out here so that all of you can go back and help evangelize this information. Okay? Port mapping, in other words, how often does that NAT kick out at state or that firewall kick out at state, right? Make sure that's more than 60 seconds would be best. For people who say, there are some ISPs that says, well, that BitTorrent stuff, I don't like it, I would depreference it and put it into the sandbox so it gets worse behavior than other connections and stuff. As we mentioned, BitTorrent has started using Teredo. Okay? So if I want Xbox to have a good experience and somebody's making BitTorrent have a bad experience, wouldn't it be great to distinguish between those two categories? So currently, you can distinguish between those. And that's because Xbox One will prefer, if it's available, port 3074 for the actual data traffic. Okay? And so by prefer, that means if you got 2 Xboxes in your house, some of you raise your hands and said 2 Xboxes, you're having a LAN party and you got 2 people there, only one of them can get that port. Okay? The other one's going to have to get something else, right? And so if you're the only Xbox, then you'll be using 3074. If you got more than one of those will be slightly better than the other one. In other words, the one that's slightly better might be designated as the host. Okay? And so what that means is that if you're at ISP or you're doing ACLs or management or something in a campus network, then 3074 is the one that's used more for gaming traffic. Now what we don't know is how long it'll take BitTorrent to start doing the same thing. The more open the NAT, the better. So in terms of NAT choices, there's a couple different types of NATs. Some are better than others. Okay? There's actually 2 sets of terminology that both mean the same thing. Address independent means you get the same mapping and the same filtering for everybody that you're talking to. Address dependent means you might get a different port for each person that you're talking to and so forth. So there's different things here. It says you really want something that's as far to the left as possible in this taxonomy of terms, which I'm not going to go into details here. Okay, more details in the references. All right, now we get into some discussion that relates to carrier-grade NATs. One of the common scenarios when you have a carrier-grade NAT is that you have 2 Xboxes that are talking to each other, but they might be in different homes, right? Even if I've gone through some lobby service, I'm not playing with somebody else, he happens to be down the street, but he's still in my neighborhood. We're behind the same carrier-grade NAT because we're both got the same ISP, okay? And so what happens here is the traffic used to go out my house, go up through the ISP, and come back to me. Okay. But as far as the matchmaking service goes, it found out the IP address that I'm known by the rest of the internet. If I'm playing a 3-person game, I still have the IP address that's seen by the guy that's not in my neighborhood. Right? We're all using the same information. And so what happens is the traffic goes out of my house up to the carrier-grade NAT, turns around, and comes back in their home. And this sort of shape of traffic here is called a hairpin, right? Because it's shaped like a hairpin. It kind of goes in one interface of the NAT, gets translated twice, and goes right back out the same interface of the NAT. Can also happen on your local LAN, but usually, I should say, the same traffic here would not normally happen in a home, because in a home, once you're on the same LAN, it will just go direct without going up through the NAT, right? It's smart enough to do that. Okay. So this is mostly for CGN carrier-grade NATs to say you want ones that support hairpinning. Some do, some don't. In that CGN requirements document I talked about yesterday, this is one of them. Okay. Finally, if you're using Teredo, this is actually what the packet format will look like. If you try to take a network sniff and look at what the packets look like, this is what you'll see. So going from the left to the right, so from the first byte to the inside. So on the left, you'll see the IPv4 header. Okay. Then you'll see the UDP header. Okay. And again, usually if you're looking at data packets, you'll see 3074 in the port there. Then after that, you see the IPv6 header. Then after that, you see the ESP header. Right. So this is where it's using transport mode, IPsec, inside IPv4 UDP. Still transport mode. Okay. After the ESP header, the rest is encrypted. Where you see application data and trailer. I should say it's encrypted. In some cases, it may be authentication only. ESP can be used either way. So as I mentioned, native IPv4 will be used if it's available, but generally for like LAN play cases. Okay. And so what we see is that to all the middle boxes in the internet, things look like IPv4 because that's what's in the outer header. They'll look like IPv4 UDP port 3074. Okay? That's what most ISPs and exchange points will see. So when we look at exchange point statistics, that's going to be Xbox traffic. UDP IPv4 port 3074. However, we all know this is actually using IPv6 end-to-end. All the applications are pure IPv6. Okay? So again, at least 98% of the time, if not almost 100% of the time, Xbox One will be all IPv6. Okay? This is different from Xbox. In Xbox, it was about IPv4. Xbox One is all about IPv6. Okay? Because it's the thing that provides end-to-end, peer-to-peer connectivity. Right? It is the future, IPv6. That's my plug. Okay, so for any other questions here, you can ask me. There's also a website that has always had IPv6 information. We're putting more Xbox information up there. That's microsoft.com/IPv6. You'll find white papers that go all the way back to XP and stuff there. And you'll find more information about Xbox that we'll put up over time there. And various other RFCs that talk about things that I've presented out here. Okay. So with that, I'm happy to take some questions.
Will you be backporting some of the stuff into the 360 or previously?
I'm not able to announce anything, so not that's been announced anyway. I should also mention that I'm not I haven't been in the Xbox group, and so I've done consulting for the Xbox group. Now, recently, Microsoft had a reorganization around the the operating systems group. So now we're all together in one operating system group between Windows, Windows Phone, and Xbox. You may have seen some news about that. So now I guess I can say I actually am in the Xbox group, or at least the part of the Xbox group that doesn't do the gaming platform, it does the operating system platform, which includes the Trado portion, the IPv6 portions. Okay, I'm now in that group based on the recent reorg.
Have you done any examination on the failure mode between Teredo and the native v6?
Yeah. You want to know what so this is not about Xbox here. This is about where does that 40% or more come from. So Jeff Houston has done some, we've done some. Some of it comes down to two categories of things, and there's probably some other smaller effects. So one effect has to do with the routing that's used, right? So when you have the relay, you have to advertise a route to the Trado prefix into the backbone of the IPv6 internet. And similarly, it has to have a IPv4 route that's advertised into the IPv4 internet from the left side. Okay? Both of those routes can be flaky and filtered in some cases, okay? Because they're not seen as being high enough production because they're not tied to a single like AS number, right? So Hurricane Electric does a good job of making it as being as reliable as they can. They're not the only relay, but they actually do the best job. The second reason is at least as big, probably even bigger, and that's the way that red line works. Okay, in order to set that up, can I go all the way back to that slide here? I can point to the this one. Okay, so you see that red line there that shows a relay. This picture is a little bit misleading. This one is showing it as if there is a single relay and it's a symmetric route. It's not. Okay, these are regular routers. In regular routers in the middle of the network, right, you have asymmetric routes. Okay, so that means in the forward direction it might be using one relay, and in the reverse direction it's using another relay. So what happens here is that when the packet goes in the right direction, right, so from the left to the right in the IPv6 internet, in order to initially establish the communication, so this is like the equivalent neighbor discovery or ARP or whatever, it actually sends something that comes into the right as an ICMP v6 echo request. In other words, it's doing the ping, is what it looks like to the guy on the right side. So he doesn't know anything about Trado. This is the native v6 internet. Okay? If he does not respond to pings, he doesn't find the right relay, and stuff doesn't work. Okay? And so it comes back to people that filter ICMP v6 pings or that don't respond to ICMP v6 pings. And that's actually the biggest contributor. Okay? And of course, there's lots of information about what you should or shouldn't filter, and people who just filter everything in ICMP because it's ICMP, or they don't like pings, they don't like being, scanned or whatever. So at the edge of the network, they just block all pings or whatever. That's what is the most of it. That's what's most of it. Okay. But again, all that pinging, the ICMP stuff is only for the red line, and on the blue line here, there's no ICMP traffic. Okay, that's the main reason why there's a difference.
On the order of operations, where you went through Teredo to Teredo, and then native v6 to native v6, and then v4 to v4, you said that's public or directly reachable V4 to V4 only? So does that mean there's no stun or turn or ice or anything like that?
No, and correct. So IPv4 to IPv4 is when, so there's no stun or anything like that. That was true for Xbox 360, but you won't see any of that on Xbox One. Okay. With Xbox One, the only thing of that like is Teredo, which is just using v6. For IPv4, it's if you have an address, and the guy has an address, and you can get directly between those two addresses with no NAT in between, that's the v4 to v4 case. Okay. So that means either it's public v4 to public v4, or it's private v4 to private v4 behind the same NAT. Okay, and that was the second one's the LAN play case. If I'm both on 192.168.0.2 and 192.168.0.3, that's the v4 to v4 case if IPv6 doesn't work better.
So for the IPsec keying, is that keying actually terminated on a Microsoft device and then re-encrypted and back out to the endpoint?
It's end-to-end.
Is it end-to-end?
It's completely end-to-end, yeah.
Okay. How is that managed? Is that encrypted AES or
don't know.
By default?
I can find out for you, but I don't know off the top of my head.
Okay.
If you send me email, or actually if you look on that link there, it might actually have that, but I don't know which one it is. So I'm sure you could easily find out faster than I could if you actually tried it on after the 20 seconds. So yeah.
Two questions.
Yeah.
One, you only ever see an ESP extension header behind an IPv6 header.
Correct.
So there is no issue about CGNs and ESP. And
That's correct, right? So Karsten is pointing out that on the packet format slide here, right, regardless of whether it's native v6, in which case the first two won't be absent, or will be absent, or whether it's native v4, in which case the UDP and IPv6 header will be absent, it's always ESP. The case that you're using IPv4 to IPv4, okay, you'll still see an ESP in there. Okay. Now, some of these things, the actual heuristics used to say pick between the three categories here, whether Teredo, IPv6, or IPv4 is used here, I say use the one that's better. Okay. The actual heuristic for which is better will probably improve over time. So whatever it is right now, whatever it is 6 months from now, it'll continue to be improved based on experience to say, because it basically has two components, loss and latency. And which one of those tends to be more important may vary based on experience with what kind of games we see and what kind of experiences we see. Okay, but those are the two things. But it's still using ESP.
the other question, you said we have 2% good IPv6 right now. No, both sides have to be good IPv6 to make this happen.
Yep.
So is it 0.04%, or do you know anything about the correlation there that would make that percentage higher?
What's that?
2% or 5%?
Okay. So Karsten's question goes back to this picture here is the statistic that it's 2% of customers, or is it 2% of end-to-end traffic between customers that have V6 and customers that have V6? Or is it like 2% of 2%, or is it just 2%? These numbers come from World IPv6 launch and later, those statistics, and I believe they are 2% of traffic, but I'm not certain.
They should be client to server,
Yeah,
right?
I see other people nodding that that's correct. So this is not 2% of customers, this is 2% of traffic, but I'm getting that from others, right? This is not a Microsoft stat, this is a global stat that has been shared around, so.
Just game with the right people.
Yeah, just game with the right people was the question, yeah.
Is the Xbox to Xbox introduction protocol, is it published or is it proprietary?
When you say introduction protocol, you're talking about the matchmaking part?
Yes, the matchmaking.
I believe that one's proprietary because I don't know that there is a standard for that.
So is that just making use of IPv6 literals or some other name resolution process?
No, it's basically passing, it's not literals in the sense of string form, but it's IP addresses in the sense of there's no DNS being used here. Right? The matchmaking service does pass around IPv6 addresses directly.
So even on LAN to LAN, it's not doing like link local multicast name resolution or anything else?
Correct. There's not name resolution here. So that actually reduces the set of dependencies here. It doesn't matter whether your DNS is hosed or perfect, right? It'll still work.
Are you using link local on local network, peer-to-peer? Or are you using the global address?
I don't know for sure offhand, but I can tell you that the answer to that may vary over time.
Wireshark, okay.
Yes. Whatever the answer is now, whatever the answer is next year could be different, and since this is going to be recorded and be replayed for a year, you should be prepared for the answer to be either way. Okay, got that online? Okay. I mentioned that the heuristics will be improved over time, right? So that's within the realm of things that may be improved as you see patches and stuff based on what the games actually experience.
Is that it? One more? Oh, Joe, you're killing me. Here's the last one.
Privacy. You're actually combining both the IPv4 and IPv6 on both sides. How are you going to apply that, considering you're going to be monitoring every connection endpoint for Xboxes?
I'm not sure I understand which question that you're asking here with combining. What do you mean by combining?
Using the matchmaking service?
Yes.
That's going to provide both IPv4 and IPv6 addresses for every device out there.
Yes. Well, it'll provide, okay, so now I think I understand which question you're asking.
You're actually storing it, or will be storing it.
Microsoft is very big on privacy. We try to store as little as possible. There are some cases that there are logs that things are logged as far as who logged in, because we get subpoenas and things. So let me tell you a personal story which affected me. About 2 years ago, my home was broken into, and I had a couple devices stolen. I had 2 laptops stolen, my wallet, and an Xbox. Okay. Now, the other things, the police couldn't find any way to track down. The Xbox was the only one that allowed them to catch the crick, and that's because what the crick did was he took the Xbox, he sold it on Craigslist to somebody else. That somebody else then plugged it in and turned it on. When he plugged it in and turned it on, it signed in with my Live ID, or my Xbox ID. Okay? When it signed in with my Xbox ID, it had actually authenticated as me, right? When it authenticated as me, it got logged with what IP address it came from. When they took the IP address it came from, the police subpoenaed the Xbox group, and they give out that stuff to people who give subpoenas, right? And so then they could track down the exact IP address of the guy who had it. They went and interviewed the guy who had bought the Xbox, and it went back from there. Okay? So there's some logs and stuff that happen that they do for cases like this. Separately, your question is about what you give out to people. Okay? So what is logged is to say, Dave Thaler's Xbox account, his Xbox Gold account logged in from this IP address. That's logged. Okay. As I mentioned, I personally am very happy that that's logged because that allowed them to track down the guy where nothing else. Otherwise, my credit cards didn't have any. They wouldn't have found them through my credit cards or anything else that was stolen. As far as what's given out to peers and stuff, on the other hand, what's given out is, by the way, the matchmaking service found that these particular IP addresses are within a decent RTT of you, and they kind of match there. I'm not going to give you somebody that only has good connectivity with native, and you only have good connectivity with Teredo because you guys are not going to have a good experience, right? And so I'll give you a set of them that matches there. And so when you say it's combined, if I already know which one is better, I may or may not give you both the IPv4 and the IPv6 address of their guy. So you might not be able to correlate between them. Okay, so the matchmaking service gives out as little information as possible, and we log as little information as possible. We do log some things, and actually I'm quite happy that they did log that. So.
All right. Wow, the gaming got the most questions. Go figure.
Game on.
Game on.
November 22nd.
How many folks have one ordered? Anyone? All right, a few folks. All right, cool. Well, thanks so much, Dave. Right. Appreciate it. I'll let you go ahead and do that. This, and I'll go prep your. Pardon? I think we're just straight on. Give me a second to go ahead and get things set up.
IPv6 is good this now. Everybody is Xbox One should be running IPv6 account.
Are we up? Can you give me a click forward just to make sure that that actually is great? All right, that is working. All right. Give folks a few seconds just to settle in here, just to get plugged in. Let them take seats. It's fine. All right, I think we'll go ahead and kick off. Next presenter, who's, and I double check, is it Karsten?
Yes.
Karsten Bormann?
Bormann.
Okay, all right. And you're going to have to help me with the university name. Is it Bremen?
Bremen, yes.
Yeah. All right, well, I'm not doing too bad then. Not completely slaughtering it yet today. So scaling the web to billions of nodes, this should be interesting because, you know, those of us that are starting off with V6, most of us are probably doing this in home labs, don't get a chance to really scale at the large scale, so I think this will be an interesting opportunity to hear about making things large and scalable. So with that.
Thank you. So I think we have had a pretty good introduction by Dave, who took us into a world where we already have IPv6. And I'm not going to talk about anything that could be called transition. I'm just assuming we have IPv6 in this talk. And we get there, it will take us a couple of years. But I want to talk about what happens when we have that and when we build the Internet of Things on top of that. So I will give you a pretty quick tour through the standardization in this area. Quick means I have about 30 seconds per slide, but of course you can slow me down if that's too fast. So the background, of course, that's the canonical Ericsson Internet of Things slide here. The background, of course, is that we have been connecting places originally by laying wires to places. Then we started connecting people by giving them mobile phones. And that immediately increased the number of endpoints. And what we are now doing is connecting things, and that will increase the number of endpoints some more. And Ericsson is throwing around the number 50 billion. Cisco, I think, has number 31 billion. These numbers sound impressive. They're actually extremely boring if you think 50 billion means 7 devices per person. I mean, who of you has less than 7 devices on you at this point in time? Yeah, it probably will go well beyond that. But for now, it's a nice milestone we can talk about. So we have to scale things up. That's interesting news for the people who run networks. But when I talk to them, they just give me a blank stare and ask, what's the problem? We can do that, no problem. So that's done, I'm assuming. The interesting other point is, who's going to pay for these 50 billion or 500 billion or whatever nodes? So you actually have to scale down the nodes to make this a reality. And that's maybe the most important point here. I mean, these are the nodes that we are talking about. This is the Canadian cent here, by the way. And this is the kind of node that will be very common. And it will be in kind of everything that has a good reason to have power, have a battery. So we have to make sure that these little things actually can be meaningful citizens in the internet. And to enable people to pay for them, we have to reduce their cost. And much of the cost of these devices comes from complexity. So in the end, we have to work on reducing complexity. And that's a really new thing for people who work on the internet. So far, we just have put layer on layer on layer on layer on layer, and things have become ever more complicated. And we now suddenly have to look back and say, how much of all this stuff do we need? What can we get rid of? So this is really what the standardization activity in this area is about, managing complexity. And you have to relearn a couple of terms you may have forgotten. There actually is a monetary unit called cent. And that's very important for describing these kinds of systems. These are the 50-cent systems. It's not the $100 systems that you are used to today. It's about cents. It's about kilobytes. I have students who don't know what a kilobyte is. They think the smallest unit is a megabyte. And it's about megahertz. It's not about gigahertz. So we have to be modest in the requirements that we actually put on these systems. So we actually try to come up with a terminology for the devices that we are targeting. And we have defined a number of classes. Class 0 is kind of the class that is too small to be a meaningful citizen on the internet. Class 1 has about 10 kilobytes of data, of RAM, and about 100 kilobytes of code space. So that would be a quite constrained node. You cannot run Unix on that thing, and you really have to run a very special operating system with some highly optimized code. But you can get very cheap chips that already have all the connections on them, so you can build cheap systems. And then there is maybe a second class, the class 2, which has half to 1 order of magnitude more, in particular more RAM, which is really a big point here. and also more code space so you can run more complex things on it. So when you talk to a meter manufacturer, they're probably going to think in terms of class 2 systems. But we will have a lot of systems that really want to be cheap and need to work with those class 1 systems. And the important thing, these classes are not moving the way we are used to with Moore's law. Because all the wonderful things we get from Moore's law get put into energy usage, lower energy usage, and lower cost. So these classes actually have been pretty much constant for the last 9 years. So since about 2004, if you just look back chip families, these classes are kind of immobile. It's now moving up a little bit. And we are getting 32-bit CPUs, so that's really a help in engineering these systems. But the classes kind of remain constant. That's very, very surprising for people who come from larger systems. Okay, so this is what we call a constrained node. Of course, everything is constrained. We don't have unconstrained energy or power or whatever. But when we say constrained, we really mean as constrained as this stuff here. Now this should be advancing a slide. Yeah. So just for people who are old enough, this is approximately the processing power that we are talking about here. This is a PDP 1134. Yeah, they're 40 years ago, and 35 years ago, and this goes in there. So those people who have tried to run the internet on one of these machines know that it was difficult. It was not something that could be taken for granted. The next problem is those constrained nodes also bring constraints with them that have an influence on the network. So the nodes need to sleep a lot. They get networks that get on the order of 100 kilobits per second, but this is not 100 kilobits per second on an Ethernet. This is 100 kilobits per second on a very lossy radio link where you never know whether your next packet will go through. There are some physical layer packet size limits. So this is a very different environment, and you cannot take your existing application programmer knowledge for granted here. There are several radios that have these characteristics. The Zigbee radio 802.15.4, Bluetooth Smart. I'm not talking about Bluetooth, I'm talking about Bluetooth Smart, Bluetooth Low Energy, Z-Wave, and the DECT Ultra Low Energy that is coming out now and will be in just about every home gateway within a couple of years. So these are the networks that we are working for, and the whole thing could be called constrained node networks because it's really about running networks that contain mostly constrained nodes and maybe one or two more powerful gateways. There are lots of terms for these things: Internet of Things, wireless embedded Internet, low power, lossy networks if you're really focusing on the networking aspect, IP smart objects. So I'm not going to take a side here. Internet of Things seems to be the term that is winning, but it's also the least focused one. So some people think a Raspberry Pi is part of the Internet of Things, and I don't quite know how to refute that. I mean, it's certainly also true. But this is not the one I'm talking about here. Okay, so we have these really cheap devices, and then we come with this old clunker called IP and try to make IP run on it. Why are we doing that? The reason is that IP gives us a way to integrate things. So yesterday we have seen all those silos, Lonworks, and the BACnet and whatever. And IP really is the integration protocol for this. It really makes it possible to put things together. And you have seen I've already talked about 4 different radio technologies that will be in your homes before too long. So we really need IP to make this happen. And where do we make it happen? Of course, in the IETF. So I will talk about IETF activities in this constrained node network cluster. There are 6 working groups in the IETF that are in this cluster. I have 5 of those on the slide. Xavi will talk about the 6th one later on. And they are nicely organized in layers. So we have one working group which is doing the internet area, talking about adaptation layers, IP over foo. We have one working group doing the routing, we have one working group doing the application protocol, and there is a very new working group which is optimizing existing security protocols so they work better in the constrained space. And then there's a fifth working group that essentially just generates informational documents that explain how you can implement all this, because it's new to many internet developers, and it is a good idea to have documents that describe this. Now the IDF has some 100 working groups, and some of these actually actively help us. So for instance, the TLS working group is actively looking at the requirements from the constrained node network space. So I will run through those first three working groups because I don't really have time to talk about security, and discuss what we have done, starting with the network. So the network is the 6-LoWPAN working group. Oh, I forgot to mention that the 6-LoWPAN working group is just undergoing a name change, which in the ITF is done by closing down the old working group and opening the new working group, because the old one was focused on wireless personal area networks, 802.15.4, and we want to signal that we are open to all kinds of radios. But the technology is usually just called 6-LoWPAN by the people who are working on it. So I haven't seen anybody show this picture, so I thought I could show it here. This is when the last IPv4 addresses were distributed, and somehow the people on this picture look really happy. Do you notice that? So IPv4 is done, and we want to use IPv6. So when we defined the IP over foo standard for 802.50.4, we didn't even start defining how to map IPv4 on it. So it's IPv6 only. 802.15.4 is a radio that was originally defined by IEEE in 2003, has undergone a number of revisions. The most likely version you will find in the chip today is that from 2006. It's marketed as Zigbee, but Zigbee is not just the radio, it's a whole silo. We're not interested in silos, so we're not calling it Zigbee, although Zigbee by now has picked up our specification and it's part of what it's called Zigbee IP. So a typical number for this radio, it's a 1 milliwatt radio. There are versions in the sub-gigahertz and the 2.4 gigahertz bands. The sub-gigahertz is different between regions. I've only put 2 regions here. There are even other regions. And the 2.5 gigahertz, 2.4 gigahertz region, of course, is worldwide. And this is an 802 network, but it's not Ethernet. It really doesn't feel like Ethernet. It has 127 byte packets, multicast works radio range only. So a lot of work was needed to make IP work on that, to make IPv6 work on that. But first of all, you have to do boring things like basic encapsulation, define how exactly you find the IPv6 packet in the radio packet. Then you have to do fragmentation, because the minimum MTU, the minimum maximum transmission unit of IPv6 is 1280 bytes. Then we put in some stuff that is read on this slide, which I'll explain how we have replaced that since 2007. And I think the great idea here was to say 802.15.4 is a nice MAC. It has a lot of functionality, but we're not going to use very much of that because we're trying to stay independent of the MAC. And that's why this standard 4944 actually applies so well to the other radios as well. So that actually was already approved in 2007, and people have started building systems on it. For instance, the ISA 100 system, which is used by what used to be called the Instrument Society of America, but which is now a worldwide organization, that uses this standard. At some point we decided the header compression that was in the original document was not really good enough. You can do header compression in a stateless way, which means you only exploit the redundancy within one packet. There is not that much redundancy there, so it's not giving you as much of a gain. Traditional header compression, like robust header compression and so on, is flow-based, but we don't have a flow of temperature readings that could be meaningfully identified on a router within a local 6LoWPAN. So we invented something new, which is based on a piece of global context state for an area that is distributed in the area, and that helps the nodes compress the 40-byte header down to something between 2 and 7 bytes. So the IPv6 headers are not big for us because we just compress them down to something much more manageable. Oh, the picture just shows your garden variety installation in a home or in an office where you have a backbone link and might even have a gateway out to something else. But don't take this gateway here. We don't have gateways in this world. Yes, good point. We have to fix this slide. Okay, third item. You all know about neighbor discovery. Neighbor discovery is a great protocol on a network that has multicast, but it turns out multicast is difficult in these constrained networks because lots of nodes are sleeping and they're just not hearing what the other guy is saying. So we had to rethink neighbor discovery a little bit and came up with something that is called 6LoWPAN ND, which doesn't use multicast at all except in the initial discovery of a router. I mean, somehow on a network you have to find out who you are adjacent to. But from that, we take it using unicast messages. So in the neighbor solicitation, neighbor advertisement messages, we have an address registration option, and a node registers, a host registers to its nearest router using the address registration option. So the initiative is inverted. It's not like the router seeking out the host, because the host will be sleeping and not hearing the request. The host, when it's awake, talks to the router, here I am, and I will stay here, but please remember me. So this is really the big change. And that's actually interesting because even in Ethernet, that makes sense. So there is now an activity called efficient ND to port over this optimization to Ethernet environments like in a data center. The other thing that 6LoWPAN ND does is distributing the context information that the header compression uses. So when a host comes up in a 6LoWPAN, it gets the information that allows it to efficiently compress the packets. So we have put this right here, so we don't need another protocol. So this is what we now have. 6LoWPAN essentially is RFC 4944 from 2007 with a couple of deprecated parts, plus the new document for 6LoWPAN header compression and the 6LoWPAN neighbor discovery. And that's a solid basis to work forward on the host router interface side. And that's what we call 6LoWPAN. Now that is actively being used, and just as an example, there recently was an Etsy plug test for 6LoWPAN. Other organizations are running interoperability events. For instance, IPSO has been running them, ZigBee IP has been running them, and so on. And of course, ISO 100 has been running their version of 6LoWPAN for a long time. So this is out there, and people working with these radios know what's it about. As I said, we have other radios, and we are now in the process of writing up the specs for that. Bluetooth Low Energy is essentially done. We are just waiting for a channel assignment from the Bluetooth SIG. They're always a little bit difficult to work with because they Well, it's their specification, and if somebody comes and says, hey, we have this little piece, just put it in, they start thinking, should they have done it by themselves and so on. So this takes some time, but the document is there. Z-Wave actually has its own radio, like Zigbee has 802.15.4. Z-Wave has G9959. That's an ITU standard. So Z-Wave chose ITU for standardization. Bluetooth has its own standards organization. Z-Wave chose ITU. ULE is done in ETSI, like the rest of DECT. We are doing a lot of standards organization shopping here. But there is now a document that defines how to do 6-LoWPAN on Z-Wave, on the G9959 radio. That's nearly complete. It is scheduled to become a working group document in a couple of weeks. And finally, the DECT ultra-low energy is interesting because there is a DECT chip in just about any residential gateway these days, and the newer DECT chips will have that. So it's something that should, a gateway for which should come at zero cost with newer home gateways. Now this will probably take a couple more months because DECT ULE itself is still in the process of being finalized.
Any thought about cognitive radios on this?
Question was cognitive radios. Well, do a standard and we will interface to it. Yeah, so this is not supposed to be an exhaustive list. This will go on. For instance, there is a wired standard as well, MSTP, which is based on RS485, part of BACnet, and we are interfacing that as well. And it's going to go on. Whenever there is anything that is useful in this space, we will interface to it. So as I said, there is a new working group called 6-Low, which is doing all this standardization. We just had our first working group meeting last week. And yeah, there are other IETF working groups that may not tell you very much that we are working closely with. Okay, so this is the internet area. I'm not a routing guy, so I'm going to make the routing part short here. There is a routing protocol for this space. That doesn't mean you cannot use RIP if you want. I mean, there are actually deployments of 6-LoWPAN with RIP, that people do that. But it's not exactly optimized for that. And the Ripple protocol is optimized for this space, in particular for networks that take a mostly tree-shaped form. It's actually not a tree, it's a directed acyclic graph, so you can have multiple parents. But the idea is that many networks are just rooted in something that provides the external connectivity, and it just makes a lot of sense to organize a network around this root. Ripple exists in 4 modes, 2 of which are entirely theoretical. There is a storing mode, where essentially every router keeps a map of its subtree. That is implemented in all the research implementations of Ripple. And there is a non-storing mode, where you really can use class 1 nodes as routers because they don't have to keep all that state. And that's implemented in the industry implementations. We have a little bit of a disconnect here right now and have to work on that. But it's pretty clear that non-storing is going to be the mode that is used in most environments that work with really constrained devices because it minimizes the state everywhere except at the root at the cost of slightly more inefficient internal packet transport. So there's lots of stuff coming with Ripple, like the expected transmission metric and so on. There's lots of good stuff here, and this has been moving things forward a lot. So Ripple is based on the route over concept. Route over means that really all the devices that have a routing role in the constrained network there are 3 routers. You can do the same thing at layer 2. You can run a layer 2 mesh network and use that. That is usually called mesh under. And there are always battles between the mesh under and the route over groups. The advantage of route over is that you actually can combine several technologies into one network. And with all these technologies out there, and Powerline, I haven't even started explaining all of them, it really makes sense to be able to put them into one network without having to make boundaries where the technology boundaries happen to be. So if your smoke detector is wired and talking to something else, so why would you have to leave the network and enter the network again and so on? So that's why route over is the concept that we are currently focusing on. But that doesn't mean mesh under is dead. Mesh under can be very, very efficient when it's tailored to a specific radio technology. Okay, so that was a very quick run through the network layer. Let's talk about the application layer some more. Now, again, this is about scaling, and when we were starting to think about scaling, we thought about what is really the application that scales well. And of course, many applications scale well, but the web is kind of the poster child here. And the web also is quite similar to what you actually do in an Internet of Things, because you are requesting information from a node, and that's pretty much what the web does as well. So the web actually has three components. HTML, now that's actually not so useful for us. We have to work on new data formats because thermostat is not going to read the HTML page of a temp sensor. That doesn't make sense. We have URIs. URIs just work in our environment. And we have HTTP. Now, HTTP is the universal protocol. It has almost replaced IP. We are working on turning that back a little bit. So when people look at this traditional stack, this is the Internet protocol stack, they look at what we have, where we have lots of media. We have two network protocols, IPv4 and IPv6. We have essentially two transport protocols, even though there are a couple more to choose from, and SCTP is getting some love recently. And on the application side, well, we have HTTP. So now if you look more closely, what's interesting about HTTP is not the actual protocol. That is rather chatty. Your typical HTTP request is some 500 or 700 bytes, and you don't want to spend 4 or 5 6LoWPAN packets to move an HTTP packet. But what you really want is REST, which is the underlying model behind HTTP. So we have HTTP in mind, but we are not using HTTP, but we are using a tailored protocol. So sometimes people ask us, why didn't we use compressed HTTP? Now the reason is you can compress HTTP very well, but you get all the bugs of HTTP plus the overhead of compression. So the amount of complexity you need to make this run just doesn't work very well in a constrained environment. It's going to cost a lot of battery, takes a lot of code, generates a lot of interoperability problems. So what we instead did was look at the objectives again and then do this kind of thing here. And the result was the constrained application protocol. This is essentially HTTP, but based on a 4-byte UDP header and not on a chatty text-based protocol. So it gives you get, put, delete, post, the things that you know from HTTP, but it doesn't use all the complexity of HTTP. It doesn't even use TCP. Implementing TCP also is already a significant complexity. So we go right on top of UDP and then DTLS for security because we need security. There's the 4-byte header, and we have one addition to HTTP. There has been a lot of discussion in the HTTP camp about how to get events from a server to a client. And there are various ways of doing this, long polls and server events and so We have a very simple notification architecture to do that. That is called observe. So you can send one request and get a number of responses in sequence with the newest state. You would use that to read a temperature sensor. It will send you a new message for every change in the temperature. So working with CoAP really feels like working with HTTP, because you have to be a little bit cognizant of the limitations. You shouldn't do video over this. It's really for small pieces of data. If you do video, your system is probably complex enough that you can run HTTP, so go ahead doing that. But for small pieces of information, like the ones that we use in constrained nodes, that's exactly the protocol that you want to have. So here's a little bit, in the ITF we like these diagrams, as you know, and this is a request and a response. So this is the 4-byte header, 2 options for the authority and the path. This is the response, again a 4-byte header and some information, in this case the content format and the actual payload. Okay, so this is CoAP, and the point really is CoAP is an instance of REST, so it mixes well with HTTP. You can build architectures like this one here, where you have HTTP in the unconstrained internet side and have proxies that talk to constrained nodes, all the while maybe talking to a server in the internet using CoAP directly. So they just mix and match. They're very easy to proxy to each other, and this is what will enable the web of things. Yeah, so here's an example. If we have an HTTP client, such as a cloud service talking to a CoAP server, it might ask for a light value and get that. And the next time it does an HTTP GET, the proxy might still be caching a valid value, so there isn't even a need to wake up and consume battery on the device. Okay, so there are various documents to look at. One is RFC, one is done but is waiting for 2 security standards to finish, which will happen within this month most likely. And 2 are in the process of work group last call or processing of work group last call comments. So this is the application protocol. What about data formats? Yes, we can ship around XML or JSON. In many applications, that's exactly what you want to do. In other applications, it may be a good idea to have a binary format. And we have heard about XE yesterday. So XE is a binary format of XML, which works well when you have a schema, when both sides know exactly what the structure is going to be. On the other hand, we often now do things JSON-based in the web, which is we don't rely on a schema, we just send the data, and there are certain reasons for doing that. And up to a couple of weeks, we had a little bit of hole here, because we didn't have a binary JSON. So yeah, we worked on that. Don't have time to go into much more detail, RFC 7049. And yeah, this is a table out of RFC 7049, and you can see it's not compressed, but it's still compact compared with other formats. So I think we have filled this corner a little bit. Security always has to be last. So this is my last slide. But security is not optional at all. So it doesn't make sense to build an Internet of Things with devices that can be taken over by someone who just has fun and switches off all lights in Asia or something like that. So we need a security architecture here that actually works. HTTP has its TLS. We know how to do this. And what we use the datagram version of TLS, DTLS, but not necessarily exactly in the same way that it's used in the web. So this is not about PKI and CAs. There are some new security processing models that we are working on. But talking about technology, this is all based on ECC now. We have the NIST P256 curve as mandatory to implement. So this is true 128-bit security. So when we talk about RSA, 128-bit security means 3072-bit RSA keys. And the internet isn't there yet. It's just transitioning from 1024 to 2048. So what we are working on right now is doing the processing models like authorization formats, commissioning models, and the performance fixes in DICE that I mentioned. Okay, questions?
I was noticing in your constrained nodes back about 10 years ago when I was doing a lot of hardware, the new Xilinx chipsets, which give you a large amount of intellectual property, so you could actually put some of the controllers in firmware to remove your software, hardware, your software issues. Are you looking at a much greater integration into the hardware level to get the performance that you're looking for at the power and cost constraints?
Well, that might come at some point. Right now, people are still writing software for ARM processors and things like that. But one of the reasons CoAP has this simple header is that in theory it would be possible to put it into an FPGA or other hardware implementation.
Yeah, well, we were doing that, looking at putting the entire IP protocol stack, or as much of that as we could, into the firmware, especially when you're talking about tactical radio systems and low power.
Yeah, I think you've implied the answer to this a couple of times, but what about denial of service amplification attacks? I'm just worried about a protocol based on UDP, that people can send a response, apply, request, and get a large response.
Yeah, we have a security consideration section that, of course, discusses this a lot. If we are using DTLS, we're covered, and we are usually doing unencrypted information during discovery, and there are mechanisms that limit the amount of amplification you get during discovery.
So I have a question around Zigbee IP. They just recently, I guess I don't know if it's recently, but maybe 6 months ago or something like that, they introduced Zigbee IP. Can you explain a little bit more about that, what the motivations were? And that was one big silo. Are there other silos on the networking layer that are perhaps going to be slowly transitioning to IP?
Well, Zigbee IP actually transitioned rather rapidly to IP. So the Zigbee IP stack is pretty much the stack I described here. The background is the Smart Energy Profile 2.0, which is an application layer thing, mostly for class 2 devices. So it's using HTTP and XML and so on and so on. And the industry essentially said, we have to do this based on IP or people will not buy it. So they really took in the standards that we have and built a whole stack based on 6LoWPAN, Ripple, and so on. Just the application layer is slightly different because Smart Energy is composed of slightly more expensive nodes. A meter is not a 50-cent device yet.
So they moved because their customers were telling them, we want to go to IP. Who else is left? Zigbee was a big one. Who else is in the way of moving to a completely IP-based Internet of Things? I mean,
well, I think just what everybody now runs dual strategy, a dual stack strategy. So they all have IP, but of course the old protocol doesn't go away, and the Zigbee's the old Zigbee stacks. Zigbee is not one stack; it's a brand for a number of specifications which are all different. But the old stacks are not going away, so they can still sell.
There's new stack. You're saying they all have new stacks, new IP stacks, and they all conform to the
Well, more or less, they're all working on that. So, for instance, on the Z-Wave work, Z-Wave is a really nicely integrated standard, but even they are working on making IP available on their radio. So I think that's really the trend, adding IP as another option, but not killing your existing product line, because that would be suicide.
For now, yeah.
Okay, we got one more question.
So I'm curious on when do you think Moore's law will catch up? So we've talked a lot about, you talk about constrained nodes. A typical Zigbee chip right now has 128 kilobytes of flash already. By next year, all those things will be a lot more affordable. I know there's always a new way of doing things, but a lot of times technology catches up. So,
yes.
So to me, it looks like, 10 megabit to 100 megabit Ethernet to a gigabit Ethernet, and that is better than reinventing the wheel and let Moore's law do its job. What do you think?
Yeah, as I said, Moore's law works in our space, but in a slightly different ways, because it goes into cost and energy usage. And one thing that might have been unforeseen 10 years ago is that we are seeing a lot of more Wi-Fi in this space. And Wi-Fi together with quite powerful nodes. So those people who say a Raspberry Pi is Internet of Things, those are actively using Moore's law. But again, for a light switch or the things that you will have 200 of in your home, I don't think that's a viable approach. It's much better to get the cost savings down into very inexpensive systems. That's what we are working on.
Okay, so thank you, Crescent, for a wonderful talk. So I would like to invite our next speaker, Patrick Grosset, who's going to talk to us about some real deployment cases and things what he's seeing in the field. And the folks who don't know Patrick, he's one of long-time Cisco veterans and a very well-known figure in the V6 world. Also serves as a V6 Forum Fellow. And the people who don't know about, I consider a really good thing for us being in Cisco, is one of our newest Cisco Distinguished Engineers as well. So with that, I'll toss it to Patrick. Yep.
So good morning. I think I would like to thank you, Carsten, because it's a very good introduction to my presentation. I think what I'm trying to do now is just take one example of implementation we are doing at Cisco for the Internet of Things business unit, and show real case and real use of protocol with deployment example. So if I was asking everybody here a definition for the Internet of Things, I think I will get as many responses as we have participants. So that's the reason I'm starting with a slide here. I want to say that first, when I'm looking at the IoT world, I want to make a differentiation between the consumer business and the enterprise business and the operational technology. So what we are focusing at Cisco is clearly the OT side of the enterprise. We don't look at the consumer. And what we are doing here for the IoT business unit at Cisco, we define different vertical market like manufacturing and plant, defense and oil and gas and mining and utilities, energy. And for each of them, we are looking at what are the use case for each of the vertical, but at the same time, we are defining architecture based on IP, which are cross-horizontal, cross-vertical market. And from there, that means we are building product, and IPv6 play a role for all of this product. When you look at plant switching and routing, or the data center, it's clearly, I would say, technology as usual. I'm pretty sure you have got a lot of presentation of how to get V6 done on switches, on routers, on application, and it's not what I'm focusing on. What I'm really focusing on is the new area here we call field area network. What I call field area network is clearly the last mile deployment. So if you are looking at operation and you want to put connectivity inside the street, and that clearly is the example I would be using here. So just to give you an example of deployment we are doing. So here I'm focusing on a field area network deployment for smart grid, for energy. And what you can find multiple layer. So here at the bottom, at the top layer here, you have the operation center. And for the operation center, this is where people will be running their traditional application. So meaning the advanced metering infrastructure with meter data management system. And this is where people doing the monitoring and the control of the energy network will be running the SCADA application. And clearly be aware that when you go to a SCADA server, when you look at the license, when you look at all the application and impact of modifying anything, these guys, they are not running IPv6. They are running IPv4, and it will take a very long time before they can switch to IPv6. On the other hand, if I look at the MI part, this is where we can introduce IPv6 as well, because we can now push IPv6 up to the smart meter. And the reason we are pushing IPv6 to the smart meter is because the last mile will be using the technology Carsten introduced, meaning IEEE 15.4, we'll see narrowband PRC, we'll see 6LoWPAN, and we'll see report. So that means here at the data center level, we are getting IPv6 application, we are getting IPv4 application. And by the way, when we are looking at deploying an IP network with millions of endpoints, you need network management for the operation. And this is where we are considering what needs to be done for network management regarding, for example, IP address management, firmware upgrade, distribution of configuration. Don't expect to get a Cisco certified engineer deploying routers or equipment for smart meter on a pole top. I mean, the guy has to be a field technician, and that means we need to put in place what we call zero-touch provisioning, meaning you plug your device, and the device will be fully secure, will join the network, will get authenticated, and we get the configuration. And this is where, to make it happen, we need to look at the collection of IPv6 features and make sure we can glue all of them together and do that. On the other end here, we are using any kind of backbone infrastructure. And this is where we introduce what we call the field area router, meaning there are ruggedized box. And these kind of box are the first generation of Cisco product where we're adding new interface like 15.4G or narrowband PRC, running 6LoWPAN, running Reaper. And by the way, we are tying any kind of equipment. So this is where we can use Wi-Fi, serial line, Ethernet. But at the same time, we have the mesh network here. And the mesh network means we can connect endpoint for very specific use case. So it can be a smart meter, it can be a distribution automation gateway device, it can be public lighting, it can be electrical vehicle charging station. So you have all these use cases here, and you want to leverage new technology, new physical layer, data link layer to connect all the devices. So that means here, when I look at the protocol stack, what I'm talking about, it's not this part, because I'm pretty sure you already know very well this part, but the fact that you have existing application, and this protocol has been very well defined at the standard level by organizations like IEC, and there is no way you can change them. This is what the people are using. If I look at, for example, distribution automation, people are using SCADA protocol like DMP3 IP or Modbus TCP or 6870, and they are moving to 61850, which are IEC protocol, and don't expect to replace them overnight. So you have to make sure that you can integrate and run this protocol on top of the IP layer. On the other end, when I look at metering, for example, this is where for North America and some world region, people are using ANSI C1222 as metering protocol, versus you go to Europe and people are using DLMS COSEM, which is typically a client-server protocol. So we have to make sure, once again, we can adapt all the application layer people are using on top of the IP stack. Now, here, I want to focus on technology we are using in the field. So Carsten talked about the IEEE 15.4. I want to add that 15.4 has evolved for utility domain and for the last mile, where we have 15.4G. And 15.4G and 15.4E, which are amendment to the standard, they have some benefit. They are covering new modulation like OFDM. They are covering new frequency band. But for example, one big change is the fact that the MTU size now for 15.4G is not anymore 127 bytes. It's 2048 bytes. So now we can look at when you do 6LoWPAN and you take an IPv6 packet. This is where you still need to use the 6LoWPAN header compression because you have low bandwidth network and you want to optimize the packet you are putting on the, I would say on the air or even on the wire if I'm looking at power line communication. But it changed the play. At the same time here, we have the 15.4 mark, and what is very important, there is a new standard coming out from the IEEE, which is a narrowband PRC, or power line communication. And narrowband power line communication, or IEEE 91.2, is using the same mark frame format as 15.4. So I was very surprised not to see the 1901.2 on the previous slide, because now it means as I'm using exactly the same frame format, I can use exactly the same adaptation layer or 6LoWPAN. I can use exactly the same routing protocol, report, and I can use exactly the same protocol. So that means here now we are looking at, I can justify why we need layer 3 routing and not mesh routing. Because I can mix and match different technology, different physical technology in my network when I'm doing a smart grid deployment. The fact that what we have done at Cisco, so Salman said, I used to work at Cisco as a product line manager for IPv6, but I also left Cisco in 2008, and I joined Archrock, and Archrock has been working on 6LoWPAN for a while, and we have solutions. So when we got acquired by Cisco, basically the team has been working on what we call the SDK, the Connected Grid SDK. So clearly we have a reference model which provides hardware blueprint for 15.4 RF and 1901.2 PRC. And then on top of that, we provide a stack where the stack is offering 15.4E, 6LoWPAN report security, meaning 1X and 11i for key management. And we are also using CoAP for network management. And the reason we are using CoAP is when you look at endpoint, so let's have a look at, I forgot to say something on this slide. Let's give some number, real deployment. If I look at one of the customers we have in Canada, you have one operation center, but you have 2 million endpoints. So 2 million endpoints running IPv6, aggregated by around 1,700 CGR, meaning field area routers. And here we have IPsec tunnel up to 8 SR1K. So just to give you an idea, when you are managing the network, it's an enterprise network, but the size is very similar to a service provider deployment. 2 million endpoints. So think now about how can I make a software upgrade on 2 million endpoints? How can I do address management for 2 million endpoints? So that's what the solution needs to provide. So this is where when we look at the picture for the SDK, the reason we are using CoAP is don't expect to do network management. I would say, I want first, network management is a key feature. You need to provide network management capability. Now the fact is, don't expect to do network management of millions of endpoints using SNMP or using a pull model. You need a push model. And this is clearly why we have been selecting CoAP for network management. Once again, we don't want to touch the application. People who are building meters, they are using DLMS COSM or C1222. People who are building sensor, they are using DMP3, IP, Modbus TCP, or whatever they want. So this is why the application here is fully open. But for network management, this is where we are leveraging CoAP. Now the fact that we talk about 6LoWPAN, so it's a brief review of the 6LoWPAN adaptation layer. And I want to reinforce the fact that it's not only 15.4. It's also applicable to narrowband PRC, 1901.2. So what we are doing here, the fact is there is no IPv4 equivalent. Meaning when you build a 6LoWPAN subnet, it's only IPv6. But remember what I said at the beginning, protocol, a SCADA server is an IPv4 platform. Device like a cap bank controller or any device for smart grid are IPv4 only. So one of the open questions is, how can I connect all these devices on an IPv6 only network knowing that they are doing IPv4. So that's how we need to find a solution. And here at the same time, when you look at the different header, you can see that 6LoWPAN has different header. So you put a data packet, you will have the 6LoWPAN. If you are doing fragmentation, you may have your fragmentation header. And by the way, as I said, with 15.4G, you are not limited anymore to 127 bytes. You can go up to, 2,000 bytes, 2,048 bytes. So here, it reduces the number of fragmentation we need. And you have the mesh routing. And when we are doing IP routing, we don't need the mesh routing at all. Address management. I know that we talked about in the previous presentation about the extension of neighbor discovery for 6LoWPAN. But the fact is, IP address management is only one of the elements when you are deploying the network. So let's say I want to deploy my 2 million network end node. I need to do address allocation for IPv6, but I also need to pass information to the end node like this is the address of the NMS server, this is the address of the collection engine for the data metering, or this is the address of the DMP3 server. So this is why on the solution we are implementing, we are using DHCPv6 with a rapid commit option. So we want to limit the number of messages. And at the same time, we are also using the vendor option. So we can pass information like this is the address of the NMS server, this is the address of the DMP3 server, and you can put whatever you want. So clearly, here, if I look at the gateway or the router which is connecting the 6LoWPAN subnet, I can act as a DHCPv6 relay, which is very well known. Its features. And I can look at the DHCPv6 server here, and I can manage all information regarding not only IP address management and the other option. And you will see that it's very important because now, once again, remember, I want to find a solution to integrate IPv4 on top of 6LoWPAN. So I need to find a way to pass some information which may be sent through DHCPv6. We talked about the report protocol. So it was defined as by the IETF as layer 3, meaning an IP routing protocol. And the benefit for us, when I look at just what I presented, I can use exactly the same routing protocol for both RF and PLC mesh. Once again, if my gateway here is attached to the facility center, I may be using, V2 prefix injection. I can be using BGP, ERGRP, OSPF, or whatever you want. And guess what? We have been doing route for distribution for years. So I can take all information from report, put them in OSPF, in BGP, and do dynamic routing. And that's something very important because now I may have one LoWPAN network here, but I may have multiple LoWPAN networks. And by the way, when I'm doing RF mesh, or even when I'm doing PRC, if you can switch the circuit and redirect the power line connection, that means now one node which is attached to this router here, the day after can be attached to another router in another substation. So that means the IP address will change. But now I need to consider what does it mean for the application. And this is where the fact that I can do route for distribution just is a mechanism. Because if I was doing layer 2 mesh here, it's exactly like people running ATM PNNI. How do you do the PNNI mapping with IP routing? I'm pretty sure people remember some of the challenge we had in the past trying to do that. So that's the reason we are clearly looking at the routing layer, at the layer 3 routing. And by the way, when I look at all the scenarios from report, you have the different scenario, meaning what I call multi-point to point, meaning all the method here try to communicate with the AMI server or the distribution automation gateway, try to communicate with the SCADA server. What I call point to multi-point is the fact that the server tries to communicate with all the method, all the device, all the endpoint. And in some cases, I may have point-to-point, meaning here I may go to one node to another one, like for example for distribution automation. And all these cases have been satisfied by the report. So let's take a report deployment, a real one, for power line communication for smart grid. So here is one of our pilot. What we have done, we put the field area router here. and you start deploying all your smart meters, and you are using PLC. And now the fact that even if it's a physical wire, remember that on PLC you have a lot of noise and interference. So basically, you have the transmit power, meaning here the red line, it means these are all the meters which can correctly communicate with the router as one hop. But this one here, which is around 400 meters, there is no way when you look at the transmit power of the PLC signal due to regulation, due to some limitation like the implementation, the power supply of the meter, there is no way this node can directly communicate with the router. So this is where we are using the Ripple protocol to build the mesh. And you can see now you have the green line here, meaning it's a second hop, and you have the blue line, meaning it's a third hop, and you have the purple line, which is somewhere here, which is the first hop. And we do that for PLC, we do it for RF mesh. So the number of nodes you may have here for RF mesh, we tested up to 5,000 nodes in one low-pan network. And I would say what we are recommending is 2,000 nodes. And once again, the number doesn't mean anything. What you need to understand is what kind of protocol are you using, and you have to do proper capacity planning. So remember, if I'm using C1222, very short messages, if I'm doing DLMS COSM, it's client server. I need one connection between the server and the meter. So that means here clearly, when I look at RF mesh, the number will be higher than the PLC. But if I look at C1222 as application protocol, the number will be higher than what I can do with DLMS COSM as well. And the good thing as well, I'm not showing that on this slide, but remember on PLC, you may have crosstalk. So what does it mean? It means here, I may be deploying my meter on, it's a three-phase interface, but this meter here may be on phase A, this one may be on phase B, and this one may be on phase C. At the same time, if I have crosstalk, it means one device here on phase A can get the signal from another meter on phase B. So this is where part of the protocol, the mesh protocol, using all the metrics, you have a very tight coupling between all the layers to understand what is the signal quality, what is the phase information, and that's what we can use to build the metrics for report, which is clearly different from other routing protocol we have, where you can't play with the metric like that. I talked about using multicast for the field area network deployment. Why do you need multicast? First use case, firmware upgrade. You have 2 million meters here, multiple PAN, let's say 2,000 PAN, and you want to push a new firmware upgrade. So what you can do, you can define as a network operators, I will put all these devices in one group, and now when I need to push firmware upgrade, I can do multicast. So I'm doing IPv6 multicast from the network operation center up to the field area routers. But here, we don't try to put IPv6 multicast implementation on the endpoint. Because remember what Carson said, the resources are limited. So what we are doing, we are just using the broadcast at layer 2 here to push the multicast. And the field area router here is acting as a proxy for the multicast traffic. And that means we can do firmware upgrade, but when we start looking at application, in the smart grid environment for AMI, for example, for the advanced metering, people are using multicast for what we call demand response, meaning you want to push a command to all the meters. You can do a targeting ping. You can do a reset messages, sending reset to a lot of meters. So there is a lot of application for multicast here in this kind of environment. But once again, it's not the consumer market. It's not the over internet. It's a closed enterprise deployment for operation. So now the question is, I talked about V4. I talked about the SCADA server here being V4 only. I talked about some of the equipment like RTU, which may even be non-IP at all. I mean, running serial protocol, nobody knows about anymore. But you have to connect them, and you want to connect them on the 6LoWPAN network here for RF or PLC, which is V6 only. So how can you do that? And by the way, what you want to do, as I said, this device here has an IPv4 address. The application here, the SCADA server, very often the IPv4 address of the device are coded. And this device here, which connect the RTU or the ID, can also switch from one network to another network, meaning the WPAN address, the IPv6 address will change. But the use case from the customer is, I'm buying this equipment from different vendor. You will never get IPv6 on it. Here, I'm paying a license for my SCADA server or my DMS server. I won't be getting V6 for a while. But give me a solution. So what we have done, we say, let's have a look at what the IETF is doing. There is a protocol which has been used for service provider for, I would say, integration of V6, called MAPT, or the mapping address and translation. So now, the fact that why don't we just use MAPT for a closed domain like 6LoWPAN and report. What does it mean? It means here I have my server with an IPv4 address. It doesn't change. I can do V4 up to the MAPT border relay. Here I have my IPv6 network. So I'm defining that as the MAPT domain. Here I have the MAPT CPE device. So now I can assign an IPv4 address for this device, and I can connect this one. And part of MAPT, and this is one of the reasons we pick MAPT and not MAPE, is the fact that very often this device will come configured with a private address, and all the devices will be configured with the same private address, and the operation team doesn't want to modify the address of the device. They just want to pick a device on the shelf and send it for installation. So that means now what we can do, we can put a MAPT address, so that means here from a 6LoWPAN standpoint, this device here on the WPAN or the PLC interface has two IPv6 addresses. One is a pure, I would say, WPAN address, which is purely IPv6. And the second one is a MAPT address, which maps the V4 address. By doing that now, I can do report, and report will advertise, meaning this node will advertise its route, this one, and it will also advertise the fact that this address is reachable through this one. And now, on the router here, I can do route redistribution. So now I can inject information as part of BGP or OSPF. If the node is switching from one PAN to another one, it will get a new WPAN address. But the MAPT address will stay exactly the same, meaning the IPv4 address of the device will never change, which is exactly what the application server is expecting. So now I can do PAN migration here, going from one PAN to another one. It doesn't change anything. I don't have to reconfigure anything inside the network. It's dynamic. From a routing standpoint, what does it mean? It means here when I look at the router and I do a report table, I can see the IPv6 address of the interface on the router. I can see the IPv6 address of the CP device, and I can see the MAPT address of the device reachable through this one. And if I do a route redistribution, and here I was doing it using IV2 routing prefix injection through FlexVPN, I can see the prefix for the, I would say, WPAN /64, and I can see the route information for MAPT for this given device. So that's, I would say, how we are gluing all the IPv6 feature set protocol to deliver a solution meeting the use case requirement from customer. So in summary, I would say IPv6 benefit to the IoT because we have the address space. We have, and it's very important, one of the key requirements from the industry for IoT, they say, when I'm deploying equipment, the equipment will be there for the next 15 to 20 years. So the question is, if I look at any physical and data link layer communication, give me one single communication technology which has not changed over 10 years, period. None. Even if I pick Ethernet, you went from the big thick cable to thin cable to twisted pair to 10 meg to now 100 gigabit Ethernet. Now, if I look at the IP, this is a stable architecture for the past 25 years. And that's exactly why we are considering IP as good for this kind of industry. And at the same time, you have all the protocol, and you can leverage all services which already exist to build a solution. I'm done.
So a question from online was in regards to a sleep timeout. Is a sleep timeout configurable? And
where?
I think it was, that's all they put in, but I think they had a sleep timeout question in regards to asking if it was configurable about how long.
How long, what, does it take to do convergence?
Yeah.
So remember, when we look at Report, when we look at the IoT, we are not talking about fast convergence. I mean, if you look at OSPF, ISIS, people have been focusing on how can I converge as fast as possible. Here, we are looking at, and this is one of the key characteristics from Report, the network has to be as stable as possible. We have low bandwidth, and we don't want to use all the bandwidth from the network with control messages. So whatever we are doing here, we can tweak parameters, meaning you have all part of the REPL implementation. You can play with the REPL parameter, but all the default we are putting on the platform are there to make sure that we try to decrease as much as possible the overall protocol. Right. And that's one of the reasons we may not be exposing all REPL parameter on the endpoint itself, because we don't want people to mess up with the network.
Is there any questions additional, Dave? Actually, Solomon, can I have you do that, because I'll prep the next presentation.
Any questions, guys?
Great. So you and Kirsten mentioned, one of the aspects of Ripple is that it can be used across multiple link technologies. And so among the customers that you're aware of that are actually deploying it, are you actually seeing any Ripple domains that are using multiple link technologies? Or is the primary use case that you're seeing deployment of is where they're using Ripple domains that use a single link technology?
So right now what we have seen, people are using single link technology. So it's either PLC or RF mesh. Clearly, if I want to achieve this kind of deployment, I need a layer 3 routing protocol. I don't want to say Ripple. I need a layer 3 routing protocol to do that. Now, the fact that when I look at the evolution of the chipset vendors, what they are talking about is building new chipsets where you will have dual radio, meaning PLC and RF mesh in the same chipset. And that means it will justify why you have to go for Ripple as well.
Any other questions?
So this is interesting because it takes us outside of the home and some larger Internet of Things applications. So you talked smart grid. What are some other, I guess, projects other than smart grid that you've been working on or that's been using this similar type of technology?
So right now I've been focusing for smart grid for the past 2 years. Wow. So it's very challenging for me to answer. When I look at the IoT business unit at Cisco, we are covering the mining, oil, gas, and we know there are, I would say, other opportunities here, but they may have some different requirements, and that's why the next talk will be covering the SysTish and how we can be more deterministic. But I'm expecting that what we are showing here can apply to the other vertical market as well.
Yeah, that's what I'm wondering. I mean, within Cisco, are you pursuing your own different technologies for the different industry segments, or we want
to be, across vertical. So let's take the example of the small GA gateway with the MAP-T. So clearly, on this one, you have what? You have one Ethernet port, 2 serial. That means we can connect any kind of device. So right now, we are using it for SCADA application. But SCADA applications, they are not only for smart grid. You will find them in different environments. And that's how we will be propagating the technology.
Okay, any more questions here? Okay, if not, I really appreciate Patrick you sharing us with us all the experience, and yeah, the next speaker I'll invite over here is the next speaker is Xavier, and I don't want to take a chance with his last name. Is it Villa Hosana? Okay, okay, very good. Xavier is from UC Berkeley, as you can see, and he's going to talk about the 6-dish working group in IETF. All right, thanks.
So I think I've got a very good introduction by Karsten and also Patrick, so thank you very much. Now everybody knows what I'm going to talk, and that's very good because I can focus then on the details. So I'm going to present the work we are carrying on at 6-dish. This is a new working group that was formed last summer on the IETF, and we will try to bring IPv6 connectivity on low-power industrial wireless mesh networks. And the term industrial is important here because they have some properties, they have some characteristics that make them different than current wireless mesh networks for home and for other scenarios. So this protocol stack has already been presented, and you know about CoAP, you know about UDP, you know about 6LoWPAN. We've been talking a little bit about 15.4, and now I introduce here 15.4e. Patrick also explain a little bit. My presentation will focus on a gap here that exists in solutions that you can buy from customers, but is not standard. So each customer has their own implementation of this binding layer. And what we are doing here is trying to homogenize, standardize, provide the rules so everyone can implement that in a standard compliant way. I also will introduce a little bit how 15.4e works, and I think it's important to understand how it works because it's pretty different than previous versions of 15.4, and this is why also, because the way this protocol works, we need to cover some things here. So the first thing I will present is the wireless challenges. So we need to understand the wireless medium and the problems it has, and especially in industrial scenarios. Then I will talk about 15.4e, and then I will introduce what we do at 6-dish. So the first challenge we have when we talk about wireless communications is that we have external interference. So, and especially in our constrained devices, we have low power radios and we have narrowband channels. So we are very prone to be interferenced by other technologies, and this is we are using ISM bands, so these bands are open. Any technology, any radio manufacturer can use that bands to make their chips. So we have many problems here, and we need techniques to deal with that, and especially in industrial scenarios because we have some requirements such as reliability. We don't want to lose packets if we have to stop a machine pressing a button. The second challenge is multipath fading, and this is related to the fact that waves bend when they collide with objects, or if they have metallic things around, they change their phase and they become destructive interferences. So the same wave can destroy itself because it's bending somewhere. And this is a thing that happens more when you are talking to narrowband radios. So you have your bandwidth smaller, so this effect happens much more. To understand all this, what we did a couple of years ago, it was an experiment, and what we did is we drew in a paper a kind of square thing like this with that sizes, 20 centimeters by 35 centimeters, and we took a wireless transmitter and a wireless receiver, and we sent 1,000 packets from the transmitter to the receiver separated a meter, and for each of these positions. And we computed how many packets arrive at the receiver. And we plotted that result. So as you see, this is the shape of the paper that we use. And according to the position of the device, we got from 100% packets delivered to 0% packets delivered, and only in 20 centimeters difference. So depending on where you put your device, you have lots of chances to be able to transmit, or in contrast, fail all the packets you send. And this is a thing that exists and is real, and it's on the is a property of the wireless medium. So we cannot fight on a particular channel against that. What we did later was to test all the channels, look the 16 channels and see what happened. And what happens is that the shapes that we observe are not correlated. This means that if I'm a node and I'm in a bad position and I'm transmitting a packet and I fail, if I choose another channel, I have lots of chances to be in a good position because there's no real correlation. And this property is very, very important because this tells us that using channel hopping, slow channel hopping, when we communicate, we can improve a lot the reliability of our network. And this is what 1540 uses. So they provide a lot of reliability by using this slow channel hopping. So every time they send a packet, they change channel to send the next one. So now let's talk a little bit about 1540, a little bit how it works. This is a reminder what it is. It's a MAC layer. It's an amendment of the 15.4 standard that proposes some new MAC layers, and we will especially talk about the mode called time slot channel hopping. And this was published the 16th of April 2012, so it's a pretty new standard. And it's not a new standard. In fact, it's only a revision. It's an amendment of the physical, the MAC layer defined by 15.4. What it provides is ultra-low power operation, synchronizing the modes. And synchronizing the modes is very important because instead of using CSMA transmissions, we have the modes synchronized, and they exactly know when they have to transmit. Knowing that, you save a lot of energy because you don't need to CCA and retransmit if there's collisions, because you exactly know when you have to turn on the radio. And the receiver also exactly knows when it has to turn on the radio to receive. So in that sense, we don't have idle listening nodes trying to catch the packet. And also uses, as I said, channel hopping. So the MAC layer is structured in a super frame. We call super frame the structure. That is, I split time in time slots. And also I have the 16 available channels. This builds this kind of mesh. And a node can be configured to transmit in one of these little cells. This means that if E has to transmit to C, it will transmit at time slot, whatever it is that one, and that channel offset. So this structure repeats over time. So when the time elapses, it goes here, and then it starts again. So a node follows this schedule. If it has more cells scheduled, then it will have more links or more packets. We will see that. A slot, so what happens in one of these cells? The slot starts, and on the top we have the transmitter, on the bottom we have the receiver. Let's look at the transmitter first. The slot starts and the transmitter is off, so all the hardware is off, nothing is running, except a little timer that is able to wake up all the hardware. So the timer at a certain point on time in the slot wakes up the hardware and toggles the radio to transmit the packet. And this happens exactly at this offset within the slot, let's say 2.120 milliseconds. And this is a point of time that it's known also by the receiver. So this is fixed. The receiver is sleeping, and it turns on a little bit before the exact time when the sender will transmit the packet. And this is because we want a little war time here because clocks between nodes drift. So we don't know if they are completely aligned or they are shifted by some microseconds. Okay? So it turns on and eventually receives the packet. And then the same applies to the acknowledgement. The sender waits a little bit with everything off and then just turns on with a little bit of war time to get the acknowledgement. Every time two nodes communicate, they align their clocks, because if the transmitter is expected to send the packet here at that point, and the receiver receives it somehow in that war time, it knows how far it is from the exact point. So it knows the drift between with respect to the other node. And then it can correct its drift. So every time there's a communication, nodes align their clocks. And this maintains the network synchronized. Also, 1540 defines other mechanisms like keep alive and beacons to maintain the network synchronized. And how fast the network desynchronizes depends on the crystals, on the hardware crystals you have on your hardware. So you can buy very expensive temperature compensated crystals, and then your modes hardly ever desynchronize, but you can have cheap crystals and then you need to synchronize more. So channel hopping works following a formula or a mechanism. Let's say that time slots start counting from 0, but they never end. We have like a 5-byte number that if you compute with time slots of 10 seconds, this gives us 350 years to count on. And each time slot has an absolute sequence number. The cell has also a channel offset, and then we have a particular slot offset within the slot frame that repeats over time. With that simple formula, we get the real frequency channel that we have to transmit at each slot. And this causes that in that slot frame, imagine that I will transmit at channel 11. When this elapses and I go again to the next slot frame, because the slot sequence number will have changed, then the next time I transmit, I will use another channel. And this ensures a kind of random pattern of selecting the next channel I have to use. And this is very useful to mitigate the effect of multipath, because in average I get a very good reliability. I don't lose in average lots of packets. And this is what some papers show, and this 99.999% reliability on this kind of networks. So having a schedule is very good because we can do many things here. Depending on how we schedule cells, we can have more packets per second. For example, let's say I don't know, this blue, they correspond to this. So if in a time frame I have more slots to transmit from D to B, I will be able to send more packets. I can improve latency because I can schedule nodes in a row. So I have first H to F, the second one F to D, D to B, B to A. So I improve latency. Or I can have robustness by using different links to point on different routes, and then have like redundancy on the path my data will flow. So this is a kind of summary. This is what happens in the slot and how the network operates. But what is important is that this standard does not define how we build this schedule and how we maintain it. So it says we have to use a schedule, but nobody says how we have to build it and maintain and configure that network. And this is still open. So what vendors did is they implemented the MAC layer and they built some components that do their own scheduling. And this can be centralized or distributed, but nobody tells how they do because it's a kind of private thing. So this protocol started, or the foundation ideas of this protocol started in 2006 by this protocol invented by DAS Networks. Then this evolved to another very well-known industrial standard, which is wireless HAR, and it has the same foundation. And in 2012, 15.4e took that ideas and put them also in an IEEE standard. Nowadays, in a lot of industries, in heavy industries like oil refineries, pipe monitoring and all that, they are using that technology. So here's where 6T group comes, and we try to fill the gap between having IP-enabled architecture and putting it on together, putting it over this 15.4e MAC layer. And the gap is how we can have a standardized way to schedule these networks. What are the mechanisms we need to configure the underlying MAC layer to accommodate, to 6LoWPAN, to accommodate it, to Ripple, to work on them, and all that. So this workshop, as I said, we started like private discussions in December 2012, like within people that we were in this world. And then we created a mailing list in January 2013, and suddenly we realized that we were 160 members in few weeks. So there's a lot of interest on that technology. We met like extraofficially on the ITF meeting in Orlando in March 2013. We were not even a group, so we just met there to start planning how to proceed. We prepared our buff for ITF 87 in Berlin, and we got accepted after some modifications. We were very ambitious in our initial ideas, but then we had to start a little bit slower. And 2 weeks ago, we were in Vancouver, and we started. We presented some of the draft that we are working on, and some of them got adopted as a working group document. So things are moving forward. So here's some information. There's a mailing list. It's pretty active. We have every week we have a phone call. It's on Fridays morning and 8 in the morning here. We have published several drafts which describe part of our work. And the charter of the group and the main scope now as it is defined on the ITF is to define an architecture to describe the design of SysTiX networks, so how this is architecture, how IP is put on this kind of deterministic TSCH networks. We need to define information models containing the management requirements of a SysTiX, so what's the data that we have to send to nodes to be able to configure them, what's the interaction API, what's the management APIs for that layer, and also define a minimal mode of operation of 15.4e because it's very open. So 15.4e enables everything, so we need to define or narrow a little bit the configuration of 15.4e to define an initial way to bootstrap the network and enable people to bring their implementations and interoperate. So this is the third big thing that we have to work on. And this will be a static schedule. So we are not even facing for how to do a centralized scheduling or distributed. We are only thinking now and have a static schedule and have best effort routes using Ripple on top. So this is the architecture. You've seen all this slide in Karsten and Patrick presentations. We have the low power lossy network. We can have multiple backbone routers, each of them being a root of a Ripple tree. And these will be connected to a backbone subnet, and we can have there a PCE path computation engine or element that will be able to compute the schedule of the network and send this schedule to the nodes. This is a centralized approach. We are also looking on having decentralized approaches where the nodes in the network can decide the schedules according to the application needs, like I need that bandwidth, how I schedule a path to the gateway or to the dark root of the network that meets my bandwidth requirements, and how can I do that in a decentralized way. So we are aiming to support both cases. So to do that, we define a 6-stop layer. 6-stop will be a management layer on top of 15.4e and under higher layers like 6LoWPAN. And this layer will take care of the information and data models that we will define. So what's the information we carry through the network, and convert these packets into operations and configuration to the 15.4e network layer. This is an initial set of commands that we are defining. I will not go through them, but basically there's one to create or update or delete a cell. So how I install a cell in the schedule, and we differentiate hard cells and soft cells, and these are little details. How I configure the enhanced beacon of the network. So this is how I configure how often my network advertises so others can join, and so on. So there's lots of things we can configure here. And the main objective is to support both operations, centralized and distributed. In the case of centralized, we will have a path computation engine that is able to compute the schedule of the network, and through the backbone router send that configuration using co-op to each of the nodes of the network. Then when the co-op packet reaches one of these nodes, it calls the 6-stop API, and 6-stop will take care of configuring TSCH. This is one approach. Another approach is to have it in a distributed way. So I'm a node in the network, and I have a bandwidth requirement, sending 3 packets per minute. And I tell to the 6-stop layer, please ensure that I will be able to send that number of packets. And then 6-stop has to take care of installing that packets in my schedule, but also talking to the neighbor, so the neighbor knows that I will transmit on a particular slot, because this is deterministic. So here there's a lot of mechanism on monitoring and reacting against bad links and all that. So another draft we are working on explains how, using co-op, we can manage the resources of a node. And this is a pretty simple approach based on a REST API. So each node will offer a set of URIs that will be used to configure the node. So for example, when I want to query the neighbor table of a node, I will call this REST operation with a get or a put or a post, and I will get an answer according to what I do. So we are defining also these URIs to interact with the nodes. The final step is to provide a minimal configuration. So what's the minimal configuration of a TSCH network? So others can interoperate. We define that, and it's pretty simple. We have 101 slots, so our slot frame is defined to have 101 slots. The first slot is used to advertise the network, and the next 5 slots are shared, slotted aloha approach, shared slots where nodes can either transmit or receive, but they are shared, so there can be collisions. It's not completely deterministic. But this approach is good in order to bootstrap the network, because I don't need to have any knowledge. I just start and I try to transmit in any of these. If I have collision, I back off and I try in another one. But this enables to build the ripple topology very easily. I can start getting information of my neighbors and build the ripple topology. And it also can be used as a fallback mode. So imagine that then I schedule my network, I get a path to the PC installs all the scheduling, and everything works in a scheduled way. But for some reason, things start to fail. I always can come back to this mode of operation to recover. So it's a fallback mode of operation as well. The final thing that we do is define how Ripple works on that network. And our approach is to use RFC 6552, which is the objective function 0 that defines how the rank of nodes is computed. And here we are proposing as the rank factor element of this function to use expected transmissions, which is the inverse of the probability delivery ratio. And this is what we propose, because it's the most simple approach to have a routing topology in a standard way. So, and that's it. Thank you.
Okay, guys, any questions?
Just a question about some of the techniques that are being looked at in the working group. You showed in the grid of time slots and so on how the things that got assigned to a cell was like A sending to B and B sending to C and so on. Wasn't that what I'm thinking of? But that's a fine picture. And so the question is, in terms of when a node, say C, is able to receive versus the slots when C is able to send, okay, is there discussion of trying to put the send slot as close as possible after the receive slot for cases where they're either doing a forward or a response? Yes, or yeah. It seems like you'd want to minimize the end-to-end packet latency and also minimize the time that the radio has to come up because there's some spin down time. And so is that one of the factors that's taken into account, is the send slot versus the receive slot, trying to keep those close?
So there's many different approaches, and this is part of the scheduling policy. And right, what we will do on 6TiSCH is not to force any scheduling policy, because then vendors will be angry with us. Because if someone has an implementation and he wants to be standard compliant, he has to change their implementation. And some applications of this technology are treated for oil and gas monitoring, and some others are for other applications. So the scheduling technique in itself cannot be standardized. What we can provide is all the tools and all the mechanisms to install the links that some central algorithm computes to the nodes. So we will not say exactly how to do that. But we will provide, so that the 6-stop layer will provide monitoring information. We'll be all the time looking, okay, what's the PDR of this node, what's the PDR of this node, of this cell, and it would be better to change, and it will suggest to the PC or to the distributed algorithms, okay, why not we change because this cell is not good. But also note that as this repeats over time, it doesn't matter that, well, it matters, but it doesn't matter a lot if you send here and here than if you send here. And so if you are like back, you know what I mean? So if I receive here and I send here, I optimize latency. But if I send here and I receive here, I lose only one slot because in the next one I will have in the buffer another one in queue, so I will send the previous one. Right?
Yes, but each packet ends up with an extra round.
Yeah, and then I lose memory. Yes, I lose one packet of memory.
Is there an optimization function to streamline so you have a nice propagation for, first node to last node type of thing?
Yeah, this for sure. The scheduling approach can do that, of course.
But it's not something you do. You would rely on the main
No. So we don't focus on how a central or a distributed scheduler works. We provide the tools to them to install them into the nodes. Only the communication, because vendors want to implement their own optimization.
Are there any standards that do that? No,
and I don't think it will be standards on that.
Any thought in terms of using the newer phased array or steered beam antenna technology on your multipath fading issues?
Well, yeah, there's many approaches to improve that, but you can have MIMO antennas and, many different hardware approaches, but as we are using super narrow band, the effect is always there. Because at 2.4, you have to separate antennas, I think 10 centimeters at 2.4 gigahertz. But sometimes the node is land a house, yeah. But the nodes sometimes are super tiny, so you cannot have a 10 centimeter separation on antennas.
Right. Well, you do the orthogonal.
Yeah. For sure that hardware manufacturers will do that. We focus more on the network.
So there's a question from online of if you had the 6-dish URLs available at all? In terms of the working group URLs? Those.
What do you mean the URLs?
Yeah.
Yeah, so the 6-dish is it's already a group, so you can join the mailing list. We have this homepage where we keep all our draft working. Also, we keep. I think here it's not. Here it isn't the 6-dish working group on ITF. The website is not here. So, but if you Google 6-dish working group,
the 6-dish working group. So it is up on the ITF now.
Yes.
Okay, I think that's what they were asking for. Any other questions? Let's give them a round of applause. Give me a moment to get a few things set up here for the next presentation. Bruce, did you want to do introductions?
Mm-hmm.
This is for you. This is for you. I'll get that up.
Okay, well, I'd like to personally introduce Rene Pop. Rene and I met for the first time face-to-face here. However, he was my first guinea pig for the IPv6 podcast. So I guess I'm plugging my podcast now. If you go to iTunes and you search for IPv6 podcast, I've done 3 so far. I've got another 2 in the can. However, the reason I really wanted to introduce Rene is that he's from A10. And as you notice, A10 is right here, sponsored by A10. And I think, I just want to acknowledge A10 for actually sponsoring this event because they're the ones that are paying for most of us being here today. So So with that, Renee, I'll leave it to you.
So thanks, Bruce. Like I said, or like Bruce said, I'd like to do an overview of A10 networks and our IPv6 solutions. Give you an overview of what we do right now and a little glimpse of what's coming up, new features. Slide it down. Oh, thank you. All right. So for the people that do not know A10 or do not know as well, because we have grown very fast in a very short time, do a quick overview of the company. So A10 was founded in 2004 by Lee Chen, who also founded Foundry Networks and Centillia Networks before that. And we have grown very rapidly in the last year. We're close to 600 employees right now, and I think we doubled over the last 2 years or so. So it's going very fast. So ACOS is our operating system. That's the driving force of all our technologies. It's very efficient and allows us to scale very well with the hardware we use. And the Thunder series and AX series is the core of our product lines right now. We have a lot of very well-known companies that use our products and are very happy with that. In the service provider space, a lot of wireless carriers here in the US are currently using our products. In CGN, we'll go over that a little bit in a moment. And in Japan, we're doing extremely well. We're actually #1 in Japan right now in the ADC market. And a lot of providers there are using us for the server load balancing as well as IPv6 migration technologies. And here in the US, where the IPv6 issue is growing as well, especially with large carriers. So we're rolling out in a lot of data centers there as well. But also Web 2.0 companies, everybody will see some logos of companies they know and products that they use right now. And with that, we have customers, over 3,000 of them, and in 43 countries over the whole world. So like I said, application delivery controllers is the core of our business. However, IPv6 is a big part of that, and it's running on the same platform. It's running extremely well because we have boxes with lots of CPU power and a lot of memory, so it's lending itself very well for IPv6 migration technologies. But in terms of application delivery, that can be the first step for a lot of companies, enterprises to get their introduction into IPv6 because it's very easy to connect your load balancer to IPv6 and then in the back end take your whole IPv4 infrastructure of your website and that way be quickly connected to the IPv6 internet like that. So like I said, our platform is really very capable of dealing with IPv6 migration technologies and to do so at scale. So the Thunder series and AX series are very capable of running a lot of sessions simultaneously, up to 256 million concurrent sessions, depending what platform, obviously. And this is going very well for us. So very quick on a little bit of overview of IPv6 and the adoption rate. I'm sure we've seen a lot of slides already throughout this conference, but the bottom line is it's coming and it's coming fast. And everybody start realizing they need to do something about it because more and more people bringing devices that need connectivity or an IP address, right? And the fact of the matter is we're running out of the IPv4 address space. So especially with the proliferation of the connected devices and the BYOD, people bringing their own devices to work and expect to be connected right there. So in terms of adoption rate, 2012 already we had more adoption than the previous years combined. So the percentage numbers are not that high yet, but it's increasing very, very fast. And one of the first deployments that A10 did in terms of IPv6 is in Japan, entity Plala. They had a project, Hikari TV, which was a fiber to the home project where they streamed karaoke services, and it's all IPv6 native, and they're using our services to load balance that all over IPv6 natively. So we're very proud of that to be, I mean, this was back in 2008, but yeah, we definitely like to be on the front end of the IPv6 migration right there. So the little thing we're very proud of. So as you know, very well know, the IPv6 and IPv4 are incompatible with each other, and yeah, people really need something to make the two worlds connect to each other, and that's what we're playing in with the AX series and the Thunder series. So we have a lot of technologies that I will go into a little bit in a moment. So carrier-grade NAT or large-scale NAT for the immediate relief of the IPv4 address shortage. And then we have various tunneling protocols and translation protocols to make this happen. So when you look at IPv6 migration techniques, basically they all fit in three different buckets, right? So first of all, there's the dual stack where you don't really integrate anything. You leave it up to the end device to decide where they route their packets on. So it's really separate clouds there. And then you can encapsulate either IPv4 in an IPv6 core network or vice versa, IPv4 in 6. And then we have a whole plethora of translation techniques that we support to make the two communicate with each other, which they natively cannot do. So here's a little curve that shows some of the techniques that are available and what they do. So as I mentioned, it should be the laser, the SOBPT or protocol translation. So this can be the first step for an enterprise to enter themselves into the IPv6 realm. Just taking an IPv6 address, put it on the load balancer, and this is a very quick way to be connected without any big efforts in your infrastructure on the back end that can all remain in IPv4. So the next one up is carrier-grade NAT. We had a panel discussion on this yesterday as the necessary evil or whatever you want to call it. But fact of the matter remains that it's an excellent technology for immediate relief. It aims to be the most transparent NAT technology that's out there because a lot of proprietary NAT technologies will break a lot of applications, and carrier-grade NAT is not just designed to do everything at large scale, but to do so in a very transparent way, right? So then 6RD is a tunneling protocol where you tunnel IPv6 over an IPv4 core. So this will allow your users to connect to the IPv6 internet without making big investments in your IPv6 core just yet. And then when we move up to NAT64, so this is more where we treat IPv4 a little bit more as a legacy protocol. So this way we tunnel IPv4 over an IPv6 core network and allow legacy devices that are only capable of doing IPv4 to make them connect or actually to connect the IPv6 only address devices to the IPv4 content that's still out there. There's 95% of the internet is still on IPv4. And then DS Lite is the tunneling over an IPv6 core network. So really the top of the curve is treating IPv4 as the legacy protocol. Where we hopefully can retire IPv4 very soon, right? So In that same curve, we got a couple of use cases. I talked about it a little bit already. SLBPT, very quick way to connect your website into the IPv6 realm. Carrier grade NAT to immediately relieve your IPv4 address shortage in the most transparent way that is possible in a NAT. And so 6RD, we had a customer actually that had a new supplier. They were IPv6 only, and their internal clients needed immediate access to the IPv4 mothership in Texas, actually, I believe it was. And later on, this supplier in Texas bought the supplier in Asia-Pacific region, and they needed to have a tighter integration. So NAT64 was a great way to make the users in the APAC region connect to the v4 services that were based in Texas. And DS Lite being rolled out in multiple areas in carriers right now where they upgrade their core services, but still we need the IPv4 connectivity, right? So DS Lite is a great way of making this happen and still remain that connectivity for legacy devices. So the next one on enterprise ROI. I mean, the C-level people always want to know what's it going to cost me, what's it going to cost me if I don't, and what's the ROI of IPv6. So that's extremely hard to put a dollar sign on it. We've heard comments yesterday, just wait long enough and they'll figure it out by themselves, right? But there are arguments to be made why we need to transition into IPv6. So one of them can be a competitive element where you have your marketing team can boast about being on the front end of new technologies. Definitely a big driver. We've seen a lot of ISPs that we serve in Europe that are doing this, and definitely standing out from the crowd right there, from the old sluggish big providers that are out there. And the sooner you do it, the easier it will be, right? I mean, you have time to train your staff. You don't have any panic upgrades, and which can be very costly as well. But then more importantly, it's about being connected to the entire internet. I mean, when you go to a website, this is our old A10 website. When you go there, you expect it to show up. When IPv6 users want to go to this website, which is v4 only, then you don't want this, your number one brand. I mean, this is still happening. A lot of big brand names that are outside of the tech industry have nothing on IPv6. So this is definitely a concern for them, and this is a very good argument to lay in front of the C-level people. So SLBPT, this is an example of our own website, as a matter of fact, where our ISP was not able to provide us with any IPv6 addresses, and our DNS provider at the time didn't provide Quad A records either. So one of our SEs in Holland actually is running a data center. He said, well, I have lots of IP addresses, IPv6 addresses, so why don't we eat our own dog food? We will front end an AX series with an IPv6 address, and in the back end it will load balance to the IPv4 only address. And it worked great. And we're running it still, as a matter of fact. It's going really, really well with a minimal effort. We had this all running in literally 5 minutes. It was really amazing. Next up, I want to talk about an example in the education sector. This is, I think it goes for a lot of enterprises as well, but this was here right in the US, where universities typically were a lot of IPv4 addresses, but they are feeling the squeeze as well. They got their students coming in on campuses, and they bring an iPad, iPhone, and an Xbox, and what have you. So there's a proliferation of connectivity that they need to maintain. and they were having big problems with it. So CGN provided immediate relief right there to take care of that. And they were able to host their staff and student applications over Carrier Grade NAT without any issues. All their applications were still running smoothly. So it's a great first step. And very similarly, one of the top wireless carriers here in the US did not have a lot of IPv4 addresses, and they still want to expand. They still want to connect those cell phones, right? So they currently are running in more than 25 data centers in the US, are running carrier grade NAT solutions over our AX series, and do so very well. So basically they were able to reclaim 90% of their IPv4 address space, and had huge savings when compared to other vendors that do this in very big routers only with application blades. We do all this in one rack unit box and very cost effectively, and I'll have more on that later. But also this carrier knew that carrier grade NAT is just a gateway, right? I mean, they know more needs to happen. This is not the answer. So they actually did a pilot with IPv6 only cell phones, and I think they had about 3,000 of them, and they used NAT64 translation to still maintain connectivity for these users that are on IPv6 only connection and still want to go out to IPv4 content, which again is like 95% of the internet still. And this was very successful actually, so it was a very great way for them to alleviate their immediate need and slowly move into new technologies and slowly migrate into IPv6 right there. So last year with Network World, Scott Hogue did a test of the load balancers, and we did very well there in IPv6. Mentioned there, so we were the only vendor to receive top marks in this IPv6 part of the test, and with 5 out of 5 stars. So we're very happy with that one, obviously. But similarly, in Interop in Tokyo last year, we drove the network that drives the whole Interop network. We were part of that at the core to provide all these technologies running simultaneously with carrier grade NAT, and translations was live being demonstrated and at a very large scale without any issues. So people there were able to connect to the Wi-Fi and connect to the whole internet using any technology they wanted. And we won awards for that, which we're very proud of. So let's get in a little bit more detail on our technology, on the hardware, which separates us from our competitors because we have very efficient form factor. So this is the AX3530, one of our flagship models for IPv6. And as you can see, it's a very compact form factor, one rack unit, and we were able to do 256 million concurrent sessions over this box. And the reason we can do that is we have very powerful CPUs, octa-cores, and a lot of memory that you need to maintain all these huge tables for doing all this address translation. So the platform lends itself very well for this kind of work. And in other models, we also have silicon, FPGA silicon, for doing more powerful network tasks right there. So we have 10 gig ports. Other models we have 40 gig ports coming up, and so it's very reliable. We have no moving parts in the front end of the box, so only on the back end we have hot swap smart fans and the power supplies. They can be replaced while the service is in unit is in service, and so on the front end you don't have to open up the box. So it's extremely reliable, and also with the hard drive, we stopped using regular spinning hard drive media a while back, and our RMA rates have dropped immensely because of this. So it's faster and much more reliable. So it's working out very well. And so with that, you know, the advantages over platforms, I think, is very much on our performance, very cost effectively, and in a very compact form factor. 1 RU for most of them, the really big boxes for 3 rack units for the real big carriers out there. But still, this is a very big difference from our competitors that only can do this in big routers that fill up a whole rack. And if you want full hardware redundancy, you need another one of those router filling up a whole rack. So it's a big contrast. So in terms of data center footprint and in terms of the cooling and everything else that comes along with it. So it keeps adding up. This is kind of a summary overview of the requirements that you should look for when you look for a solution for IPv6 migration. So interplay is what we mean, that all these technologies like carrier-grade NAT and NAT 6.4, et cetera, they can run concurrently. So you can phase in your migration to IPv6, and that the users that are on these different clouds can still communicate with each other, which is something that is actually quite a challenge for a lot of competitors. The failover, you definitely, especially as a carrier, you do not want your current sessions to drop if you need to provide maintenance on one box, for example, or if something were to go wrong, power outages, what have you. We have hot failover, so all sessions will continue on the other standby box, and users don't even know that something went wrong. So that's extremely important. And then through CGN or LSN capabilities, with that, I mentioned it yesterday on the panel, some vendors say we can do NAT and we can do it very fast, so it's large-scale NAT. This is really not the case, because the strength of carrier-grade NAT is in its standardization, and it's aimed for transparency, and it's got a lot of features that the traditional firewall-based NATs do not offer, such as hairpinning, for example, so that the traffic from user 1 to user 2 will loop back into the network. And almost most importantly of all, especially with all these translation technologies, is the logging. I mean, you're going to have tremendous amounts of logs when you connect users and keep the translation, and you need to keep track of them for the lawful intercept, etc. If somebody needs to track down a user who had an IP at what time, you are mandated by government to keep these logs. So we provide a lot of options to reduce these number of logs, and also to get rid of them altogether with deterministic NAT. I've got more on that in a moment. So this is something you should not underestimate, because it is huge amounts of logs that you have to deal with and that you have to store for a long time. And your box needs to be able to produce these amount of logs without impacting the regular performance of your NAT functions as well. So this is really a big challenge for vendors to do. Then new features, of course, you know, IPv6 is still new, and still new technologies keep popping up, and you need a vendor that can jump on them very quickly and implement them very quickly, because newer and better technologies keep coming up. And you know, not two networks are the same. There's not one answer that is the best one. Every network is different, and every technology that's out there can be a better fit. So you definitely want a vendor that can play in on, is very nimble and able to adapt. So data center efficiency, I talked about that, very obvious, important in terms of cost, budget friendly, but also in terms of the amount of data center footprint and the cooling that comes with it. So with that, I want to give a quick overview of some new features that we recently introduced in the last year. So first of all, there's fixed NAT. So FixNet does via an algorithm, it knows about the tables of public IPs and the inside IPs, and it uses an algorithm, so you don't need to log each transition that's going on, because at a given moment, when you know the outside IP and port number of a certain flow, you can always trace it back to an internal IP. So this hugely reduces the amount of logs that it produces. It's only one line. So this is very favorable for a lot of people. Then we have lightweight 4/6. It's an enhancement on the DS Lite. Basically, it takes the whole NATing responsibility away from the after point to the before point, or to the CPE, if you will. So the NAT is happening there, and it's bringing a lot of relief to your endpoint, so you have less choke points in your network, if you will. We introduced L3V support, so we can do multi-tenancy. If you have different routing domains with overlapping IP addresses, for example, or you want to provide this as a service to different users, so we could think about SDN. In this case, we have support for that. We can run up to 128 virtual routing domains on one box. Stateful firewall we implemented, and a RESTful API to control it. So this is especially interesting for people that want to use such kind of functions in SDN environments, and have an API to control the box with. And something that's coming up very soon in early next year is port control protocol. So this is a technique where the CPE device can communicate with the translation point and have a defined set of ports, so it can run certain services on the CPE side. So you have a predictable port number on the outside that the rest of the internet can communicate with. And MAP-E, we're going to implement MAP-E again, well, similarly to lightweight 4/6, it takes the responsibility of the translation down to the CPE with some more enhancements right there. And we got some more logging enhancements, so more fields of the HTTP header from the client that can go in the logs, which helps you trace back to the point of origin and do more smart things with it. And DDoS protection. So this is another big one that we will learn about more in this conference as well. But yeah, IP anomalies, DDoS threats are out there. They're very real, and more people have to deal with those. So we're implementing more features to prevent that as well. So as a summary, so what customers should do, we think, to make this move to IPv6 is to test your applications on all these technologies, make sure it works, make sure that you have the right application layer gateways that can deal with the layer 7 part of your transmission and translate that, so make sure that the application stays functional. And train your staff, so you have the time to train your staff on dealing with all these technologies and implement them. And start small. I mean, you can just connect your website to the internet, or do carrier grade net as a first step, and then phase in pilots for NAT 6.4 or whatever makes the most sense in your environment, and run a pilot with that and do all these tests again. And if you do it ahead of time, you'll save a lot of headache in the future when it's close to too late. And that ends my presentation. Does anybody have any questions?
Scott?
Scott Hogue. Does your SoftAX product work with any layer 2 data center interconnect technologies like VXLAN or anything like that?
It does, yeah.
Okay.
Yeah, or it will soon. I forgot the roadmap on that, but either right now or in the next quarter it will, yeah.
Oh, okay.
We've had a lot of theoretical discussions on CGN. A10's had CGN operating for a while now. So what are you seeing? What do you? I mean, is the roadmap indicative of the new directions? I mean, now that it's been running for a while, of where things are going with CGN. I mean, it's one thing to have it in an RFC. It's another thing to actually deploy it in customers. So what are you seeing from a practical point of view that needs to go beyond the RFC, so to speak?
New features within CGN, you mean?
Now that it's deployed.
Mostly in terms of logging, actually. One of the latest enhancements we did, like I said, was the fixed net. So you can or deterministic net is also what it's called. So you can use an algorithm to trace back the internal IP to the external IP import at a given time. So that's a huge thing because the logging is one of the biggest headaches with carrier grade net. With that said, it's a very popular technology for a lot of carriers and enterprises as well for immediate relief. People know they have to do something, but they just don't have the budgets to or the time to just flip the switch and go over to IPv6. It's not that simple. So it's rolling out in more parts of the world, even here in the US, where typically a lot of organizations have been provided vast amounts of IPv4 addresses, but they are definitely feeling the squeeze, and we see more and more implementations in it, and we'll continue to adapt to it to make it more easy to use and with less headaches of logging, etc. Yeah.
Any other questions? You don't want to know like their biggest customers or who they're running stuff for on the internet, or how'd you guys do on World IPv6 Day, and then World IPv6 launch? You guys, none of the hard questions. I mean, I'd be asking.
Having an easy day. That's good.
The hard questions were over beer tonight. Question for you: as far as are you certified by NIST as NIST for federal products?
I'm not 100% sure. I can look it up for you offline. I'm pretty sure we do. We have a lot of certification lists, but I don't know it from the top of my head.
Great, thanks.
So, yeah.
Anyone else? All right. Well, where are we sitting on next thing on the schedule? I think was break, right? People don't want to eat, do they? I didn't think so. You just want to go right into the next session, right? Yes. All right. Well, you said it.
Food. All right.
So where are we standing on? Same drill as yesterday. Different. Well, I'm grateful it's different food because I don't want to have the same food I had yesterday. All right. Well, thank you very much.
Thank you. Thank you. It's great to be here. Thank you.
So for those of you online, we are going to be back at 1:15. So we will be back at that point. We will play you some background music and leave the stream up, and hopefully back at 1:15.
And with that, I'll pass it over to Eric and look forward for his talk. Thank you.
Okay, thank you, Salman.
Yeah.
Always a pleasure to work with you. And good afternoon, everyone. The first session after the lunch is always a bit more challenging. So hopefully I will keep you up and awake. And it's a good choice because security is a concern of many, many people. And it has been for a long time the bottleneck to deploy a IPv6 network. But now I think the message is that if you care about doing it correctly, you will get a network which is secure and you can operate it correctly. So if you want to operate a network, there are several things very important things that are completely identical between IPv4 and IPv6. Obviously, everything related to role-based access control, a AAA server, getting some audits, physical security, they are the same, as you know. So, but that's important. You need to do it as well. I will spend a few time on how we can secure the three planes. And I'm assuming that here that everyone knows what I mean by management plane, control plane, and data plane. And again, on the top, in the small box, I really want to insist that 99% of the security is identical between v4 and v6, same threat, same mitigation. We just need to be careful for the remaining 1%. Management plane over v6. First, you can do it, right? You have SNMP, you get NetFlows, syslog. Most of the protocol used for managing a network runs over v6 as much as v4. Now we can ask the questions to yourself. Do we want to have a dual stack management plane or not? Basically, if you are doing a management plane which is both v4 and v6, it simply means that people can attack your management plane as well over v6. So basically, you are more exposed. On the other hand, and I think that's more important, you are more resilient because you, as a management people, you can reach your device both over v4 and v6. And besides my job at Cisco, I also had deploying networks with some customers, including one big university where I'm partly lecturing there. At some point of time, they mess up with OSPF v2. So they lost connection to all your routers and switches. No SSH, no SNMP. They were able to connect back over v6 and restore the configuration. So in my opinion, getting two management planes is more resilient and more secure. Routing protocols. Hopefully, all of us here in the room are running OSPF with authentication, or ISIS with authentication, and of course an MD5 hash for BGP. I hope. If it works, maybe. And it's not available everywhere. But at least that's the goal, right? So most of the things are identical in IPv6. Okay, ISIS is obviously the same protocol. BGP, you can use MD5 hash. One thing that has changed is OSPF. At the first design of FPS v3, they were removing the HMAC from the OSPF to move to IPsec in transport mode. Right? You talk about 97, 98 most probably, where IPsec was big. Okay, at that point of time, 10 years ago, or 16 years ago. The good point of putting IPsec in transport mode is that you can also not only authenticate the OSPF message, but you can also encrypt them. I'm not sure whether encrypting your routes is valuable. In some cases, maybe. But anyways, some people wanted to get basically feature parity between v4 and v6. There is an RFC 6506, which is a thing now a year and a half ago, that basically put back the authentication inside the OSPF. The only thing is not available everywhere on this one. Okay, it takes time. So my suggestion is there, do whatever you want for ISIS and BGP, pretty much like in IPv4. For OSPF v3, still use the transport mode IPsec, because that's the only thing that's available in a lot of platforms, if you are in a hurry. We were talking about lunchtime, about BGP and how to get multi-homing. So if you are running BGP in your network with your customers or with your provider, you also need to filter the routes. So Gerd Doering, which is a German ISP, pretty active on RIPE in IPv6, has got the list of basically what you should do in IPv6 filter, right? So basically what kind of prefixes you should accept. In some case, you do not want to get the very complex one, which is maybe 100 lines, but get one which is pretty small, such as this one, where basically you can reject some routes. For instance, you reject all the routes 3FFE, you remember the 6-bone, right? There should not be any route for 6-bone. We, of course, in this case, deny as well a default route. I mean, if you're running BGP, you don't accept the default route, for instance. And I put in a circle here for all the global unicast address, 2000/3 currently. The advice is to accept everything which is a prefix shorter than 48. Some studies have shown that 56 are still available on BGP, but you should mostly not rely on this. It has mainly an importance in this case, for multi-homing. And then you can look about the other one, like source routing or something like multicast. Excuse me. Now, how can you protect the infrastructure? So all the links and all the routers which are not having client on it, right? So basically, the link between your routers. Usually you do it by putting an infrastructure ACL. So basically putting at the edge of all your routers an access control list denying traffic from the outside to the interface of your routers on the inside, whether you're an ISP or an enterprise. In IPv6, there's something which is cool, right? The link local address. The one we never know really what to do with it, except for Bonjour and MDNS, that are basically the only one using it. But link local addresses cannot be routed, and nobody from the outside of your link can contact your link local. So Michael Beringer and myself, we have proposed at the IETF, there's a draft below, that on all the links within your network, you use only link local. All protocol works fine. OSPF, V3 will work fine. RIP-NG will work fine. ISIS, obviously. BGP is slightly more tricky because you need to define, of course, the neighbor there. But everything works fine. And nobody from the outside can attack your router. Obviously, there are some operational challenges because you cannot ping them anymore and a few things like this. Go to the draft. I can talk for a long time there. Last week in Vancouver, it was mostly accepted to go working group last school now. Some people do not like it at all because it's a change of paradigm, but it works fine. As you know, and I think Sam will talk about it later, ARP spoofing and rogue DHCP v4 exist in IPv6. It's called, of course, NDP spoofing and rogue array. This problem now is pretty well understood. There is an RFC 6101 for array-GAC, and the Savvy Working Group at the IETF, which stands for Secure Address Validation Improvement Working Group, has got draft and RFC there. And what even better, their implementation. Currently, you have really no excuse to deploy a layer 2 network which is still vulnerable to those attacks. For those of you knowing Mark Uzi and the THE Working Group toolkit, they know that we can do fragmentation, and we can fragment in such a way that access control list, stateless access control list, cannot be enforced anymore. So basically, this falls apart. This is a corner case, and it's already addressed by the IETF, and you can also do it in most of the vendors' equipment. So that's pretty important. You probably all remember that secure discovery was the reply of the IETF to the basically insecurities in neighbor discovery. That's NDP, as we know, plus RSA signatures, basically, to authenticate all the messages. It works fine. There are, to my understanding, there are 3 vendors doing it. And I remember 3 years ago, the first time I met Dave Taylor back in Seattle, we were talking to put this in Windows. It's still not there, and as far as I know, there is no plan to do it. Same thing for Mac OS. And now I can understand them because the switches can do it anyway. Anyway, other piece of good news at layer 2, private VLAN works. Port security, I'm using the Cisco term, but it's basically to prevent CAN overflow. And .1x works as well in IPv6. Yes, Joe?
There's a bypass for without, if you look at Jeremy Duncan's posting,
Mm-hmm.
he actually shows that
Jeremy Duncan's got a web posting, a blog posting, that you really need SendCGA along with the 802.1x to provide real resilience from a host security on IPv6 versus just one. There's some potential bypasses that we've been playing with.
I mean, we all know that .1x is not the magic answer specifically on the wide environment because we can insert anybody on site. Regarding .1x, I usually say that wireless is more secure than wide because you get WPA and then you are sure you're talking to the right host, which is not the case, of course, in the case of the wide .1x. Yeah, fully agree on this one. But it's the same for IPv4, right? In IPv4, you don't even have a solution for this. So something as well has been discovered about 2 years ago. If somebody is foolish enough to scan your network from remote, it will fail, right? 50,000 years, 5,000 years, you don't care. But it will run an exhaustion against the neighbor cache that will be filled very quickly by incomplete entries that stay for 3 seconds. And routers, whether the small one end or the big end, any vendors has got a finite amount of memory. So there is an issue there. So what you need to do is to do rate limiting on this, and preferably in hardware. And also, you need to change the implementation of neighbor discovery inside your routers. Okay. It's basically because the funny state machine for neighbor discovery is a bit more complex. You don't do only neighbor discovery the first time you need to know the MAC address, but you redo it as soon as you get stale address after a few seconds, and you need to send more traffic. So in this case, NDP is much more chatty, okay? But also, when you are under scan attack, you need to say high priority to renewal of existing entries, because we know that they were valid 1 minute ago, so mostly they will be valid, so it's worth spending time there rather than trying to discover a new one that may not exist. Okay, so that's basically the two improvements that we can do there. If you want to prevent this, again, infrastructure ACL, you block part of the traffic at the edge. And usually in IPv6, it's easy because you start again with a new addressing scheme, so it's much cleaner and better than in IPv4, simply because it's new. Something which is bad as well, and then we are a mix of control plane and data plane, is this hop-by-hop extension header. Hop-by-hop extension header must be processed by each and every router on the path. Cool, right? That's, for instance, used for RSVP or multicast. But it also means that if you are sending 100,000 packets per second on the line, all with hop-by-hop, they all go to the CPU, because they cannot be processed in hardware. That's the purpose of the packet. And then the CPU is 100%. You lose your BGP, you lose your SPF, your network is down. Okay. So you have basically two protection on this. One, you should do what you call control plane policing, hardware-based again, so limiting the numbers of those packets reaching the CPU. If you use neither multicast nor RSVP in your network, drop those packets, they should not be there. That's a little bit strict, but more than a network, that's okay. Now, on the other end, like on the last line, that's what I call a self-defeating attack. Because, of course, before reaching you, this 100 kilo per second packets must traverse the internet. So other routers in the path will go belly up before the attack reaches you. Okay. So it's not a very useful attack for the attacker, basically. So it's probably the reason why we will not see it in real life. Data plane, again. Bogons, so wrong IPv6 address. There are many of them, of course, right? Because we have not yet allocated the complete address space there. On-type spoofing exists as well in IPv6. The best way is to apply basically any system that you are using to prevent spoofing, like unicast and pfcheck, where basically, we use the fact of the existing routing table entries to drop packet yes or no. Again, exactly like in IPv4. Bogons, there is a team, a Kumri, which is collecting this list of bogons, either like an access control list or BGP feed, and you can use it. It's free. So, and there are also very, very simple ways of doing it. There are packets reaching big providers, having the source address being 2001 DB8, the prefix, or still having 3FFFE. So they are still machine-badly configured. So it's better to drop those packets. Remember, 5 slides ago, I was talking about the BGP filters to filter your routes. Here I'm a data plan, right? We need also to drop those packets if they ever happen in your network. It's not a marketing slide. Look at the date and look about the variety of products. Okay, you can find the same thing for the vendors. My point here is that since 2005, you have the firewall and the IPS. So you have no excuse of not securing correctly your data plane. Okay, we have all the tools we have for V4. They are there for V6, Cisco, and others as well. Not complete feature parity in some case, but you can at least do a pretty good job of securing your data plane. Okay, we talk about the 3 planes that we need to protect. So we've done our best with this to secure the network. So what about telemetry? How can we be sure that our network behaves correctly? And basically, we will use, of course, the same tools as in IPv4. So this will be mainly SNMP and IPFix or flexible net flow or whatever Gflow, SFlow you are using. Just one thing to note. So on this table, which is kind of ugly, I have tried to describe the ugliness of the MIPS regarding V6. So there are different MIPS, right? Whether you work on the IP, on the routing, or local implementation of TCP and UDP in the router. You had RFC 2096, for instance, for the route table in IPv4. Then the IETF has standardized RFC 2465, which is a MIB for IPv6 routes only. So you get 2 different MIBs, one for V4, one for V6. And now with RFC 4292 and the others, you have a MIB which is protocol version independent. So you have the same tree in the MIBs, then you can collect V4 information and V6 information. That's of course the way to go, because that you can compare real stuff. You can get the same number, the same matrix for V4 and V6, so you can compare them. The only bad news is that in all your management system, you need to upgrade from this old MIP, IPv4 only, to the dual stack MIP. Okay, so that's it. IPFix, which is the ITF or SFlow, whatever, that's all the field that you can now export by any router supporting IPFix. And you see a lot of things. The source and the destination address, the layer 4 ports, all the flags, couple of extension headers, and so on and so on and so on. So you get a huge amount of information that you can export. Of course, you need a collector to collect them and some kind of an analyzer that can act on them and detect a DOS attack, for instance, or something like that. And usually NetFlow, we try to get it to know what's happening in my network. But in IPv6, we have a challenge somehow. This is how to make the inventory. So if you're an enterprise, your InfoSec department probably does an nmap every day of your complete address space, because your InfoSec department wants to know which device is connected where. And then they do an nmap to detect the port and get what's there. They do it daily or weekly. Of course, we'd love to do it in V6, right? The address space is way too long. So one way of collecting the addresses of existing IPv6 entries is using NetFlow and collecting basically all the source addresses. Okay? Very simple trick. I'll come back on this later because there are other tricks, but this one is pretty simple. Scanning. So as soon as you deploy servers, specifically servers, InfoSec usually daily is trying to scan those servers to see which ports are open, which ports are closed, and whether you are vulnerable on a specific attack on Apache blah blah or PostFix blah blah. Okay? They do it all the time, every day. Over IPv4. As soon as you move to dual stack, you obviously need to do it as well on the IPv6 address, but also on the link local address, because maybe a device on the same LAN as your servers has been attacked, is owned by a hacker, was misconfigured, misbehaving, and then can attack you over the link local. So basically you need to scan 3 of them. Okay? Of course, the link local must be from the inside, the other one can be from remote. The reason is that in some cases, some programs will only work over V4, V6. If it only works over V6, in 5 years, you need to scan for the V6. And for the existing one that runs over V4 right now, you need to scan over V4. But also, you can mess up with your access control list. You can open one port on one protocol version and forget to close it on the other side, for instance. Okay, so you need really to ensure that the security policies are congruent there. So do this. Telemetry. So that to see whether something wrong happens in my network. After, next step, okay, something went wrong. One guy is doing some bad stuff. Who is he? If it's from remote, the WIS database works perfectly fine with V6. So we are all set there. That's my address, by the way. Thank you. Yeah, but there are a couple of X somewhere. So it doesn't really helpful. Anyway, now, the biggest problem for forensic is the following. As we all know, there are multiple ways of writing an IPv6 address. Uppercase, lowercase. All the three addresses there that I wrote there are exactly the same. Okay? Only the last one is the canonical one. But guess what? Even in Cisco device, right? And maybe others, in some cases we write it in lowercase, in other case in uppercase, in the configuration it with all the zeros and so on. So when you need to do correlation, when you say this IP address in my log, what is my access control list configuration for this IP address? In IPv4 you use grep or any kind of purely syntax checking, right? Easy. In IPv6 is not the case. I will give you pointers for other documentation later, but you know you can fix it. So you need to change something on your tool. And the other point is that we need to do correlation between a V6 address in some case and an IPv4 address, right? For 5 years, 10 years, it will be dual stack. So if you want to do correlation between an attack coming from the outside of a V6 and then the host has been compromised and launch an attack to the inside of IPv4, you need to do correlation and stitch all those events together. You can do it if you know the MAC address of those addresses, right? For instance. But that's a problem. Again, we can work around this, but just need to be aware of it. Now, we have an IPv6 address. How can we find where it is? We all know how to do it in IPv4, right? You look at the routing table, you know on which router it is. You look at the ARP table, you know on which MAC address it is, and then bingo, you know who is on port. In V6, you can still have to do and go back to the route to see which router is in charge of this V6 address. Many, many years ago, it was easy when people were using the EU64 because, as you all know, in EU64, it was the MAC address. Of course, now nobody is using those anymore, only nobody. So it's tempting to rely on DHCP, like in IPv4. But DHCP v6 is not exactly the same as a DHCP v4. For once, it leaves an address, in this case it was a prefix, not to a MAC address, to a client hardware address, but it gives it to a device unique ID, DUID, which is unique per device, stable between reboots. In this case, because there are multiple ways of building a DUID, it uses the MAC address, which is this place, plus time. But this could be any number. Okay? So it was also very difficult, basically, to pre-allocate IPv6 addresses because you do not know the DUID. You know the MAC address, you look on your PC, so you pre-allocate addresses in your DHCP server. In V6, on the box, there is no DUID, so you don't know.
Per interface, right?
And no. It's per box. Device unique ID. Look at this. That's my wife, Windows 7 or Vista, I don't remember. That's what she got over wireless. Okay? And this is not the MAC address. The MAC address over wireless is this. And this one is the MAC address over Ethernet. I guess Windows, when you boot it the first time, maybe you can control me and correct me, grab the first MAC address, the lowest one, or I don't know by mechanism, and use this. Device unique ID. Anyway, it doesn't change a lot. The thing is that now if you see this address, which is behaving badly in your network, you think, hey, I got the MAC address, you will not find this MAC address in your network. You will only find this one. So basically, that's if your DHCP servers keep only the device unique ID. But usually, you also get the MAC address, either because it's local or because the message has been relayed. Nothing prevents a DHCP v6 server to also keep this MAC address. But by protocol, it's not required to do it. So check your DHCP server, basically. Else, you are basically going back to the good old trick of looking every 5 minutes or whatever, but it should be very short time, to all the neighbor cache of all your routers and dump them. So you will know the v6 address and the real MAC address. That's what you want. You can do it by connecting over SSH, or in the famous MIP I talk about, there is a MIP for this. So it's easier to do it, of course, over SNMP. Now, there are also some switches that are supporting, and here I'm looking for Cisco, but I hope that others are doing the same, what we call first-stop security, which is basically how you can prevent neighbor spoofing and DHCP, rogue DHCP and rogue array. For this, we need to build, of course, by snooping the DHCP traffic and snooping some Slack traffic as well. We build a binding table between MAC addresses, v6 addresses, interface, and VLAN. Okay? So we build it for security. But we have also a way, typing this command, to send a syslog every time we learn about a new binding or we remove a binding. It's basically with this, you can get an incremental update, while with SNMP, you get every time a complete dump. So it's maybe easier to do this way. But it's the same information anyway. So summary, and to keep on time. Control plane and data plane. Management plan is easy, right, as we have seen. Control plane. Don't forget to authenticate your IGP, ISIS, OSPF v3. Consider the link using link local addresses. Read the draft that Michael Berrigan and myself have proposed to the ITF. We have all the tools now in switches. In some cases, you need to upgrade them, right? A very old switch 10 years ago cannot do it all the time. Rogue array and NDP spoofing or array flooding, you can protect them with array guard. Control plane policing, that's the op by op, remember. Data plane, anti-spoofing, same rules. Again, not always applicable in all platforms, so check. Anti-bogons, access control list works, okay. Be aware about ICMP. ICMP is really required in IPv6. Not only for neighbor discovery, router citation, and so on, but also for packet too big. PassMTU discovery must work in IPv6. Plus the ping, echo reply, echo request for Teredo if you still want to do it. Telemetry, back to the MIP. Just be aware that the MIP has got one version which is dual stack, so you need to move to it. IPFix NetFlow can be used for monitoring, but also to learn about who is in your network. Regarding the forensic, multiple addresses per interface, multiple ways to write the same IPv6 addresses, plus dual stack. So this will be a kind of a challenge. If you want now to find the MAC address bound to a v6 address, if you are on network, EU64, maybe if you are still running Windows XP or something like that, if ever. DHCP v6, but again, DHCP v6 by default does not keep the real MAC address, so you need to try to implement the logging for doing this. Else, do the periodic NDP cache. This part, really finding the MAC address, was one of the most operational issues that I've seen for v6. Before, it was everything related to the control plane with apps, rogue array, and so on. So we are really moving now. We know how to secure the network. We got products, policies, and so on to how to operate. And this issue of finding the address, what we call user attribution, is complex. For instance, in our internal network, we completely disable Slack in favor of DHCP. Because at least, even if you cannot do the match, the address does not keep changing every day. So conclusion is basically quite identical. And there are two references I would like to refer to you. Scott's and mine at the bottom, right? And on the top, together with people from Google, we are writing an RFC, currently it's an internet draft, which is mostly finished, which is about 30, 40 page about how can you secure and operate securely an IPv6 network. Give you a lot of tricks are there, how to do user attribution, the MIPS and so on, everything is there. So, any question?
I'm just curious to run it out there. I'm not seeing that yet. Does it also cover issues related to IPv6 wireless?
Yeah,
and secured? Okay,
yeah.
all right. Terrific.
Hey, why wireless, except for the issue of .1x, which works better on wireless? Yes, it's mostly the same. There are a couple of different implementation of a wireless, simply because all this route advertisement, demonstration is a lot of multicast, which is burning a huge amount of multicast bandwidth. So we try to document and transform basically all this multicast traffic in unicast, and we use usually the same infrastructure as the security measure, but it's by coincidence. It's a simple improvement we're doing more.
So nice presentation. I think not so much a question so much as a comment. You'd mentioned that people aren't using the UI64s, and maybe worth noting why people aren't using the UI64s. And so maybe the operational guidance is don't put your MAC address in an IPv6 address. In particular, we're trying to deprecate, we in the ITF are actually trying to deprecate the use of that. And for security purposes, I think there's two problems that you kind of alluded to, so we would make it be more explicit. One is that if it's in there, then it makes address scans much easier, because if I'm an attacker, I only have to pick a couple of popular OUIs and scan 24 bits of space per popular OUI. So that's one. And then the other one was, as long as I can see your IP address in a log or someplace else, then the OUI I can use to fingerprint to say, oh, your vendor is such and such, therefore you're probably vulnerable to X, Y, and Z. And so trying not to reveal that information to an attacker is a good thing. So I agree with everything else that you said, but maybe also add, and don't put MAC addresses in IPv6 addresses. Use the other mechanism that you described for the legitimate cases we need to look that up, but don't give out that information to attackers.
Yeah. And for those interested in this discussion, there is an ITF draft by Alisa Cooper and Fernanda Gaunt that describe, and you as well? Oh, sorry. I forgot about it. Where we can find all this privacy, and infrastructure right, of course.
I also like to refer to people to look at RFC 6192, which has some good examples of using control plane policing for iOS and Junos devices. So if you want to put in a control plane policing config, those are good ones that prevent your router from rebooting on you. So.
The help by help extension headers, you say obviously blocking them at the edge, but there is no way within a Cisco platform to block a range of, like, from 64 upwards, or...
No, you can, that's a vendor question, of course, but
yeah.
You can block on some platform, because the issue on, for instance, on Sub 720, as you talk Cisco, we hard coded, oh, it's op-biop, let's optimize, and put in the CPU before hitting the access control list. That's an optimization done in 2002, right? So that's wrong. On this platform, you cannot block, you cannot do rate limiting by default, except if you're using some LAN card, because then you can do it on the LAN card. But else, on most of the router, you can block HBH. So deny IP NENE HBH.
And that blocks the entire range.
It blocks the entire range. That's what you want in this case, yes.
Any other questions? I've got one really quickly. In regards to client-side devices and policy enforcement, temporary addresses versus privacy addresses. Do you recommend turning temporary addresses off? Do you recommend leaving them on? What do you do with mitigating and...
So, again, within an enterprise, okay, within your control zone as a security operator, as well as network operator, because privacy extension addresses burns CAM table and untreated NDP, turn it off. Now, of course, do not disable it within your OS, because when I'm in a location like here, in a conference, I want to keep my privacy. Now, this is my personal point of view and recommendation, right? I'm pretty sure some people disagree here. I know big organization, you know, as I explained, my employer, we disable privacy extension within the Cisco network, but not on the operating systems. I know that another one, which is nearby here, allow Slack everywhere and do not want to use DHCP. I don't know what you are doing because you have also a big deployment of V6. Slack. Okay. So Cisco is the more police company.
Any other questions for Eric? All right.
Okay. Thank you for your attention.
All right. Thanks a lot, Eric. I really appreciate a really nice talk. I would like to introduce our next speaker, Joe Klein from SRA International, cybersecurity expert, I would say. So I think he's going to tell us how V6 can help us prevent all the security leaks which have been happening in recent months. There you go.
Actually, I'm here representing, back. Do I have a clicker? Ah, yes. It's hard to go, change. Yeah, 600 megahertz. I'm actually representing Longbow because this is where my IPv6 research actually sits. I've been involved in the community for a long time. I've participated in a lot of government events. If you want to check out my blog, scientifichooligan.me, you can see comments and observations about IPv6 for the last 10 years. Okay, I have this old graphics here specifically to discuss that pre-IPv4, we got to have a flag day. We had the ability to actually require everybody to change networks. The other point I want to bring up here, let's see, laser. Here we go. If you notice, this was a flag day. All of a sudden, we saw this big increase as devices became available end-to-end. This is what we should end up seeing as IPv6 gets released from an end-to-end standpoint. For every technology cycle, we've seen more devices that need to be connected to some network. And this Internet of Things item, this is a real good slide for those that are interested. It actually breaks down each of the different categories, the service sector, application graphics, where the location is, and then the devices that are actually impacted. This really shows that there's a lot more devices that could end up with IP addresses than ever before. And we've seen lots of predictions on it. I'm not going to make any predictions. Also, Terminator days. Yes, did you know that sometime around 2008, we ended up with more computers than we did people? It's kind of interesting. And we see, based on Cisco, they're claiming, 50 billion by 2020, which is a lot of devices that have to be secured. So I love this railroad picture because this is really what we have right now. We have IPv4. We made some changes early, and it's about to go off the end. We also have IPv6. A lot of changes that were made. I think we've discussed this many times. I'm kind of predicting based on not only other people's comments. I'm predicting we should end up seeing about 50% traffic by 2018, which will be real fun. And again, growth, everybody's heard that RARs are out of addresses, so I don't need to continue on that. Here's the current strategy for IPv4 networks. What we do is we put lots of people in different rows, and we allow them to get around us and to attack us and to mow us down. Therefore, the current models with IPv4 are honestly broken. Security vulnerabilities exist every place. Honestly, when I'm doing a security assessment against a device that I want to get into, okay, by the way, I'm a red team. I like to break things and then try to fix it, work with people to try to fix it. I find a lot of vulnerabilities within the way some of these are written. I also find the development life cycle, a lot of assumptions that are made having vulnerabilities.
architectural, governance, other processes, the way things are managed, especially if an organization makes a suggestion on, hey, you know, we only have to patch once a month, although the vulnerability exists for, you know, 28 days prior or 29 days prior. End of life. We're seeing a lot of end-of-life attacks. We're seeing a lot of leaked information where vendors are compromised and information gets pushed out. We see the buzzword technology that really is focused on, you know, what does something mean? You have to ask this question. I've found lots of vulnerabilities in products. Recently at Black Hat, I went to every single product vendor. There was 80 product vendors at Black Hat, and I asked the same question: do you support IPv6, and how do you support it? Every single one said, yes, we fully support IPv6. Great. And also parity right now with the existing protocols. We see a lot of non-parity from a management and specifically a security device standpoint. Complexity that we have today is really great for the attackers. It's bad for the defenders. This is our current model. Yes, let's create a castle and moat system. This is really no longer workable. This is almost like having a castle when you have planes that can fly over and drop bombs. We have people dropping bombs on us, and we still are trying to create castles. Okay, humans are too slow. Most of the technology we have a man in the loop on SIMs. We have lots of other problems. We also have places where we don't have man in the loop, but people are actually injecting false information. They're actually forcing blocks on IP addresses and range, which then our customers end up calling our help desk and going, hey, I can't get to your website. So we've been seeing this for a while. It's becoming even bigger with IPv4 and the transition to IPv6. By the way, I only have so much time, so I'm trying to go through the slides. If you want to talk in detail about anything, please contact me later or see me afterwards. NAT is evil. I love this. This is like whisper down the lane. From a security perspective, we have no visibility into the end devices. Literally, I have been on assessments, pen tests, and evaluations of networks and found 2 or 3 or 4 additional devices hidden behind consumer routers or routers that were actually set up to hide whole networks. I mean, we found 80 devices in one case behind a network. We had no security security on them at all, no patching, nothing actually existed. This is real common. A lot of organizations, you find this only by seeing the type of traffic that's coming out of a single IP address. But NATs are really difficult and disastrous for security right now. Okay, this is from Richard Baitlick, who is probably considered the #1 person dealing with incident handling and forensics. He works at Mandiant today. He pretty much says today's job is to spot the problem quickly and limit damage. We can't stop anymore, not with the current architectural models that we've been using. And, you know, it's not going to hold. Our barriers aren't holding at this point based on the type of attacks that we're seeing. Sorry, anybody out there is depressed? Okay, so from my perspective, this is what the Internet looks like right now. We have some carrier-grade NATs here. We have some IPv4 NATs and some bypasses. We have a couple tunnels involved. The network is pretty much a mess. And from a security perspective, being able to identify where we have risks and vulnerabilities becomes very easy for the attacker if they get in our organization or environment, but very hard internally to actually fix a lot of the stuff. By the way, this is a real place. It's in Michigan. I have the information. Contact me later. I'll send it to you. Made me laugh. So one of the best documents to justify security that I have found is a great work by Ken Gears. What he ended up doing was he did a game theory analysis on 4 different items. He said, from a nation-state standpoint, what can we do to actually protect security? We can use technical, we can use military, we can use military political, we can use political technical. Well, based on his analysis, he found that IPv6 was actually a game changer from security. He has got, again, within the document, it has some really good definitions that you want to take a look at. In addition, he found that Sun Tzu doesn't work, so the military-only solution. The deterrence mode, you know, my cyber weapons are bigger than your cyber weapons, so, you know, you can't attack me, I can't attack you, is really failing in the domain right now because there's no attribution on who actually launched that cyber weapon. And also arms treaties that have been attempted several different times, they're failing because, again, you have no attribution. Individuals can't be tracked back to an organization many times. Great paper. If anybody's talking about, if you're with a security operation and you want to actually show some of the benefits of IPv6, this is a great paper to talk about how IPv6 with the SSL and IPsec implemented really improves security. So currently we have two survival modes if we look at our bodies, okay, because the current models are pretty much broken. What we have is a fortress model, and we have the organism model. The organism model changes quickly. It looks for vulnerabilities. It looks for other things. Currently, we have very few products in this space because the development of products can take 18 months in many cases. Patches, we know, take 30 days from some vendors, if ever. So, our current models, again, are pretty broke. So if we use these two models combined, we end up discussing a strategy that's now referred to as agile or resilient security and security architectures. What they've done is, there's a little hand down there. What they've done is they've broken up each of the different categories and actually started defining how these categories can be applied. I've further gotten into this and have applied many of the more advanced features of IPv6 to show how some of these can be used as extremely great defensive weapons that currently we really aren't taking advantage of. Recon, weaponization, delivery, the exploit itself, control, execution, and maintenance. Here's where the real problem comes in. How long does it take from a exploit to a identification currently? Does anybody know? Right now, 9 months according to the Verizon report, after we've been exploited with compromised hardware, which is called supply chain, or with an APT, an advanced persistent threat, which may be criminals, or maybe nation states trying to steal intellectual property. So this is a real problem. And the only thing we have right now is from a recon standpoint, we're seeing so much noise on IPv4, there's no way of identifying anything. It's just all noise. For weaponization, we're not looking out. From a delivery system, many times we can't even see that packet in real time. We can catch a few of them, but we're not catching a large majority of these attacks. Exploitation takes about 100 milliseconds. But when we're using models where net flow actually updates in 15 minutes, an adversary can get in and out of an organization and exfil the critical documents within that time, leaving the incident handling and management legal with interesting questions that they have to answer, which is, why weren't you able to do anything about this? So these attacks are becoming automated. They're becoming very fast at this point, and a lot of the systems that we have aren't really doing a great job. By the way, the cost of mitigating actually becomes quicker as you can actually identify reconnaissance techniques. So let's take a look at reconnaissance. With IPv4, we have a relatively small address range, and it can be scanned very quickly. Does anybody know how fast the current IPv4 internet can be scanned? Yes, the whole internet is actually scanned every day, but a new tool just was released that essentially 20 minutes you can scan for a single port for every device on the internet. Okay, that's pretty quick. That means and again, this was assumptions that we've made that, hey, nobody's actually looking people are actually looking. If you start monitoring who's doing scans on you, you'll find out that you may find that, oh, it's Patch Tuesday, and all of a sudden your scans start going up. Or you've made a product announcement, all of a sudden your scans go up, looking for you to make that one mistake, apply that wrong access control list, whatever. This is becoming pretty severe in many organizations. With IPv6, we have, okay, this is in the cloud, right? I didn't include cloud with the discussion at least once. We have a lot more addresses. Currently, the methods aren't 100% possible. Methods are actually leveraging mistakes that we make, like use of the word the dead beef, or use of sequence number or port number makes it easier to find these particular devices. Use of a address plan that isn't fully fleshed out, which makes it very easy to say, oh, half of it's going to be this and half of it's going to be that, so I'll scan for this network and this network. So decisions that you make during your address planning can actually make it easier to discover devices. That's why I really recommend talking to the IPAM vendors that allow you the ability to move things around. So recon is real interesting because from a reconnaissance standpoint, we have three types of organizations that are reconning you. We have brokers. We have brokers that scan you every day and a few times a day in some cases. They're looking for vulnerabilities on your systems. They're looking for changes in your patch levels or looking for whatever. What do they do with that information? They sell that information to not only adversaries, but they sell it to pen test teams, to security teams, to governments all over the world. So this is a real common practice. There's dozens of companies that sell this information. We also have worms. So if we see certain types of traffic, we know they're worms. Unfortunately, we haven't seen any real worms on IPv6, so we don't have any real models to work with. Although there's a real good paper from Matt Blaze discussing how difficult it can be. The third is the adversary itself. If I know that the adversary is fingerprinting my address directly from their source address, I can start using that information in many, many different ways. Now, I also want to mention from a recon detection, we have this problem. Has anybody ever heard of cybersecurity intelligence? And one of the other discussions that I had when I was walking around Black Hat is all these companies were saying, hey, we have cybersecurity intelligence. We can tell you the IP address that the bad guy is at or where a bad server is at. They're still thinking in end-to-end internet in many cases. None of them at this point support IPv6. There's no mapping between IPv4 and IPv6 publicly. There is essentially no reference that carrier-grade NAT actually exists, so now just applying one IP address access control, now 100 customers end up giving you a call to Amazon or whatever and say, hey, wow, you just stopped 100 customers from coming to my business just from that one access control. We also have the virtualized routers and virtualized web services, which I can have hundreds of web services on one physical server. So we have a lot of crazy things. It's I actually gave it the Cyber Snake Oil Award this year as far as effectiveness, because these provide some information, but most of the time they don't even, in many cases, they don't even discuss endpoints for IPv6 tunnels. Sometimes they have Tor tunnels, but they're missing lots of information. They also, a lot of them don't have references to BGP hijacks. So if somebody BGP hijacks, what they do is they'll put an address range on the blacklist, even though it may not really be where the spam came from or where something else came from. So this is considerations when you're looking at these particular products. Deception projects. One of the fun things I have been doing on my test network that's exposed to the internet is I have a bunch of V4 and V6 addresses, and with V4 I don't have enough addresses to really move devices around. But what happens if I can create random address ranges? and have devices start and readdress themselves every once in a while, maybe once a day, once every few days. Why this is interesting is two things. Number one, with some big data analysis that I now have tools on, if I see somebody going after my IP address, I know that a broker actually sold that information. So all of a sudden, I have more information than they do at this point. I know that they've been there before, and they're going to someplace that doesn't exist, which means then they're going to do a DNS lookup to find out where my IP address is. If I see that a couple times, I can block them on my DNS. So I have a lot more control than we've ever had before. Unfortunately, this isn't something that the general population is looking at from a security perspective, because again, this resilient stuff is very new. Also honeypots. Why not have, if you're in a cloud environment, you put up 10 systems. Why not throw honeypots in after those systems are up, after they've been moved from a DNS standpoint, and see if the attackers go after it? Provides you a lot of intelligence, also provides you a lot of information that you didn't have before to do trackback and traceback. Maneuvering. We can maneuver within a network and within external network ranges. We can change specific ranges. This is easy to do. Great with software-defined routing infrastructure. Makes it real simple because there's APIs that are programmable that allow us to move things around. But the ability to avoid DDoSs, not just sit there and deal with them, it really changes the model that we're thinking about. Hidden topology. Thank you, Eric, with the use of the link local. TJ Evans and I have had discussions about this. He thinks that you should support traceroute no matter what. Well, my attitude is, well, I have to make a decision from an architectural standpoint what information I want to let public. If I have traceroute, that is a piece of information that if somebody then tries to attack that particular device that has an address, that tells me a lot of information about, hey, that might be an insider, an insider leak, or that's something else. So there's a lot of information that can be gathered from this process. And again, the topology hiding in some cases may be from one direction or another, depending on use of ULAs as an example. Internal, you may block access to certain people being able to test across routers or whatever. Okay, the multi-crypto checkpoints. One of the really cool things about IPv6 is extension headers. With IPsec, we can have recursive extension headers that are IPsec. So I can actually terminate to a guard point to get into my organization, and to get in maybe accounting, I may require 2 specific keys or additional security measures that I can use. IPv4 didn't support this. This is very cool to be able to provide a gateway to gateway to gateway to host or end connections to be able to access a system. So now you can provide really virtualized isolation of certain accesses, again with access control and such. And then my favorite, active defense. Has anybody heard of active defense? These are techniques called hackback. Legally, there are concerns about this. There are trade restrictions to do this. There are treaties that may impact your organization. But the more interesting part is there's products out there that do this. Products like, essentially you leave within your organization a bunch of servers that are virtualized. It may be one server that you've attached multiple addresses to. Somebody breaks into it, it has a lot of falsified information. It also has web cookies and other components hidden in the PDFs, Word documents, whatever, which provide you traceback on who the attacker is. Also the ability to do a traceback, or somebody's pulling an HTTP query to throw a web bug in it, which is usually a 0 size or 1 pixel size image that you can find out where the actual source of the attack is coming from. These are techniques that are questionable. They haven't been challenged in legal terms today, but they're very, very interesting. Let me go back one. One of the other things about maneuvering that I've found is if I infect one of my systems with an APT, Advanced Persistent Threat, and I move that system, the attacker actually has a connection to that system and it's moved, their assumption is always, wow, the system just crashed, I'll come back later. But if I have actually moved that system has to then try to make a callback to the attacker. If I see that callback happen again, I can very quickly identify and isolate that particular traffic from an APT. Again, these are techniques we didn't have with IPv4, we now have with IPv6. And because I have to stand on the little X, I'm not running around and jumping around or anything. Some of the problems in the security space. I have interviewed or talked to so many security geeks that pretty much are ignoring IPv6 at this point. Many times they don't even know it's in their network, which is really problematic because their tools that they're sensing, their intrusion detection systems or IPSs, their firewalls aren't detecting any of this. So they have no logs, they have no insights at all that something's even on their network. And it's still even happening today. Mindset currently, I've listed the majority of problems. Also a real interesting one, and I've heard it mentioned 3 or 4 times during this conference, is a IPv4 scarcity attitude towards IPv6 engineering, which IPv6 is really an abundance type of engineering. I have lots of addresses. There's a lot more I can work with. It's a bit of a problem. Also, has anybody had within the audience, okay, and the people playing at home, you too, has anybody had their security people start from day one as you're trying to migrate IPv6 to get involved in your process? I've yet to hear of anybody that I've interviewed for the last 5 years that security is actually stepping up. Therefore, from a security perspective, some of the decisions that are made actually impact the capabilities of security. As an example, the addressing system, going with one IPAM versus another, or doing it on a spreadsheet, or whatever method, that provides a lot of internal intelligence that they can't take advantage of in an automated way, which is very problematic. Decisions on the routing or knowledge about using IPsec for OSPF as an example. A lot of those decisions aren't made, which is, real disastrous. Also, a lot of the network engineers are the ones that are getting trained in IPv6. There's really very few classes that focus on the 35 job categories that are currently within the cybersecurity domain. A lot of them are not focused on how does an auditor, an incident handling, or forensics engineer, or reverse engineer use this knowledge. Vendors, a lot of old RFCs are being used. That's always entertaining. Problems exist. Procurement, most organizations really need to make sure their procurement process includes and requires IPv6. The federal government's done it. Corporations need to do it. And also vendors test their products. You'll be real surprised about assumptions that they make. This is actually the whole product problem space. There's lots of detail. This is actually being included in my upcoming book that will be out this summer. These are all issues and problems that exist. The security people need to understand what all of this is and how it impacts their organization, how it impacts their operation, how it impacts their people, and how they need to be trained. Tunnels, the same thing. Currently, we have lots of different tunnels, and we won't even deal with covert channels. Detection of port scanning right now is relatively poor. Products like Snort great product for IPv4, but it was really meant for an IPv4 age, unfortunately. It still doesn't deal with a lot of the IPv6 NIST, maybe in 3 or 5 years. Assure 6, something I've been involved with. They have some great signatures, but it's only signature-based. I want to announce today publicly, and you at home too, that I've been working on a signature behavior and protocol analysis tool using a product called Bro, which is open source. I'm going to GNU3 the results, but I've actually mapped all the major security tools so we can detect them and be able to detect all these tunnels within your organization. Please contact me at the email address when you want to be informed when it becomes available. It'll be up on GitHub probably January because I have some additional testing and some polishing of the code. I found out that I misspelled a bunch of words, a whole bunch of other issues. It's pretty funny. Let's see, Active Recon, here's some defense tools, current research, cognitive radio, and also IPv6 on automobiles. And also, you may want to be aware that there's a new security engineering guide from NIST. I'm in the process of trying to map what the requirements are for IPv6 into that document. And that's it. I think I'm within the 2 minutes. Any questions, comments? See, I was going to go deep technical, but I only had 50, half an hour. Please contact me afterwards if you have any questions. Any questions at all? You guys are no fun. I was expecting at least TJ to pick on me. Well, thank you.
Thank you, sir. Steal that. All right, so we're going to take just a short, quick break because Sam's actually going to be doing some demo stuff with some laptop gear. Is the tables connected together, or are they? So we're going to set some stuff up in the front. My apologies. It's a little bit of a clown act going on. Just kidding. So we're going to have an actual practical demo showing off Sam blowing up a couple boxes. Yeah, the camera can tip, so we can have these facing back. So we're going to get the online stuff set up so that Sam can present remotely. Take a quick few seconds. You can do a bio break, maybe grab something really quick while we get this settled. And then right after this, we're going into the panel discussion. So we'll clear this off and get going. So give us a few moments.
Yeah. Right. I would accept that.
Personal email on there too for you.
All right. I'm going to hork one of them. I see the mic's on. Good. All right. All right. That's the target. All right. So I'm going to present from right here, right, Ed? I will take a look. Let me just start this thing. Control-Elite. Okay, good. Now, I've been made the presenter. Good. And show my screen. That looks like progress. All right. Good. All right. So I think that'll do for starting. Shall I just go?
So the other one that you want to share?
The other one is called Sim. Yeah, but only later. And how do I get this thing out? I just shove it out of the way here. Still sort of weird. All right.
So the other one I made a panelist and share.
Yeah, okay.
Should be able to